So my name is Fernando Cervantes. I work at the Jackson Laboratory. I work as a systems analyst, basically helping researchers to integrate deep learning analysis tools into their image analysis pipelines, which in the case of large-scale biological data, it has become quite a challenge. So this is why we have been looking for tools to help us to tackle those challenges. And this is how we end up with this kind of tutorial that I would like to share with other people that could be interested on applying this kind of analysis. And today, there is Peter too that is going to help us. So if you have any issues with running the code that we are going to be using today, you are free to stop us and ask any questions that you have. So I would like to start with the motivation of this workshop tutorial. So basically, we can think of, I would like you to imagine the deep learning inference process where you have an image that you want to apply some deep learning inference model, and you want to get some output from that model directly from your image. There is this idea that you will probably just take an image and send that to your GPU with your model already on that, with some code related, and you will get your output from that. Of course, there is an issue that is related with the memory on your GPU. Of course, if you want to move your whole image, it must fit in your GPU memory. Something that, for now, it is probably not possible for these kind of images. We can think that these images are huge. I'm thinking on this specific image modality, that is the whole slide image. Those are basically microscopy images that tend to be tens of thousands of pixels per side, depending on the magnification of the microscope. So it can double that if you think that you have like more magnification on your instrument. And this is just a 2D image with 3 channels. That could explode if you think that you can analyze 3D image data, 3D volumes like CT data, or if you are using modalities that can load like multiple channels, something probably in the tens or probably hundreds of channels that are generated through these instruments. So this is probably not feasible right now. So the approach that most of the tools that are around there use this idea of, well, take your image, break that into small tiles, and then those tiles are what must fit on the GPU memory. Then you will have this like inference workflow where you have a batch of input tiles that are taken from the image. Those are processed through your model to you get back into the CPU, the output of the inference. And then those are put into an intermediate buffer where you collect all the small patches, and then you have to stitch and then probably manage some overlaps on the objects that are in the edges of those individual patches. And then you apply probably a post-processing step that nowadays it is not only the inference model output that you get, it is probably something that is going to clean the objects that are obtained from the output of this model, depending on the task that it is performing. You can think that if you are doing a segmentation task, this post-processing is going to take, for example, removing small objects or removing objects that are from a different size that you have given your model to analyze. And then after that, you will still need this post-processing output to fit in memory. So still, this is not a full solution. You can think that, again, the problem of where we start, that moving the full image into memory was already an issue. We will need to tackle this in a different way to make it more efficient. So this is the approach that I'm going to be following during this tutorial, and it is leveraging some libraries that we have in Python, for example, Dask, that can allow us to get access to efficient parallel computing on patches of the image. So in this case, we will take, again, our image and break it into small tiles and process each of those in the GPU memory, and then apply any post-processing on those small tiles. And what we have nice from Dask is that it's going to stitch those together for us. So we don't have to manage this stitching or buffering. And ideally, you will be storing that directly on disk, because you can think that you have mostly unlimited disk storage, at least compared with the memory RAM on your computer. So this way, you break the problem into smaller pieces that you can address using this approach. Other piece of this is introducing the use of next generation file formats that allows us to store in an efficient manner these kind of images. So these file formats, take as an example the OME-SAR, take an image, again, break that image into small tiles, and then store those tiles as individual files in your file system. That way, when you want to access those in a specific region, like an example here, you will only need to load those specific chunks from your disk that are required for analyzing this region, and you don't need to move everything into memory. So there is a nice integration between SAR and Dask that streamline this chunking of that you have already when converting into this file format. So you can think that, going back here, those small tiles are something that have been already converted using this conversion into the next generation file formats. So there are like some steps that you don't have to handle because that would be like a more standardized process where you convert your image into these kind of file formats, and then you can apply any inference pipeline using Dask to parallelize that. So this is like the motivation of this tutorial. And I would like to, probably before starting, show you the outline of this tutorial and how we are going to manage the time. You can check this, all the materials in the website that I mentioned. You can go either to the my GitHub repository and directly to the scaling up with Dask tutorial. This is the GitHub pages, or directly to the repository and then look for the top right corner, the link to this website. So we're going to take some time to actually code. So the idea is to give you like some insights of coding that on your own. So we are going to be using some examples of how to use Dask so we can familiarize with Dask before jumping into using that for inference of large scale images. We're going to have some examples, and then I'm going to give you some time to go through some exercises on your own and showing you later the solution or proposed solution. Then we're going to move into actually implementing this inference function that is a graph around the model that we are going to be using to analyze the image. In this case, we are using as use case the cell segmentation task, and we are going to use the cell pose model. And later, we are going to put everything together and send this computation to a Dask cluster to allow us to apply this cell segmentation task on a whole slide image. Then the idea is to have some breaks between and jump into some conclusions and other questions that you could have at the end. So the idea of how this is set up is that you can go either to, if you're running this locally, you can go to the notebooks, and then you will have the empty notebooks with the instructions to follow. I'm going to be scripting that along with you. You can download those as a Jupyter notebook and run that locally. Or we are going to use, we are going to show you how to use this on a Navary. But this is the idea is that if you come later, you can do that on your local PCs. And then otherwise, you have there the solve version of the notebooks that either you don't want to take that much time typing, you can just come here and copy the blocks of code and pasting that in your notebook and run those. Or you can just check if the results that you are getting are what you expect to have. So let me jump to Navary now, so we can start setting up there some stuff, because we are going to be spinning some environments, and it takes some minutes to complete. So I have already registered and accessed the Navary platform. And the idea is that once you are here, you're going to click the Jupyter Lab module, and it's going to spin up the environment. So let me know for those who are going to be using Navary, if you are already here and have already clicked on this, or if you are having issues, let us know. Yep.
I jinxed it, because I said earlier that this is my second time that I've with no technical difficulty. I jinxed it.
You might need to restart your presentation to get it show up there. I'm sorry about that.
Yeah, no problem. I'm going to just move this here. Thank you. yeah, so Peter mentioned it's going to prompt you to select a server option. With the coupon, you should be able to select a T4 GPU instance. So it's going to give you access to NVIDIA T4 GPU for accelerating computing. And then you can start that, and this is what is probably going to take some minutes to start. So while this is spinning up, I will probably give you an overview of what is going to be installed in that environment.
Can you make it a little bit bigger?
Yeah, that's. Thank you. So there are going to be some important packages that we will need installed. Those are already in the Navari, but if you are installing those in your local computer, I will give you like why do we need those. We will need Dask, of course, for parallel computing. That is going to allow us to manage larger than RAM computation. We're going to use the SAR library. That is basically the API in Python that allows us to interact with next generation file formats, such as the .sar file. And we're going to use the TIFF file. Those are 3 Fs there. That is a package that allows us to open bioimage files. There are like a very wide of formats supported. Those are mainly proprietary file formats. So what you can do with this library is opening that file format that is in an original wherever extension is. It doesn't need to be a .tiff. It could be like SBS or NDPI or whatever extension that is supported. And then there is a nice way to streamline that as if it was a SAR file. So we are going to use this particularly to mimic the SAR file format without having to convert an image. This works for some computations, but we are going to need ultimately something that is in the SAR format to operate nicely with Dask and the distributed computing. And finally, Cellpost, this is going to be our deep learning framework that we are going to be using this time. We are going to be using Cellpost Model 3. They have recently dropped a 4 version that have like transformer-based models. But for purpose of this workshop tutorial, we're going to be using something that is Cellpost 3. That is also like, it was very well welcomed by the bioimage analysis community because of all the examples that you could handle with that model. So this is why we need those packages. Also, for those who are running this locally, it would be nice if you can go and download some test images. This is for you to have something to play with on your computer. We're going to use an image that we are going to download for the first session, but then we have also a pre-compute crop from one of those images that we have already converted to SAR file, and we are hosting that in a remote cloud bucket. And we're going to use that for the second part of the materials. So let me see if my Jupyter Lab is ready. Yep. So you're going to see this on your end. For me, I have testing this, so it is already downloaded, but you will need to look for my face and then download that environment. This is going to clone the materials that I showed you into this instance, and then we are going to start from there. And of course, if you are running this locally, you can either like go to the website and download the notebooks by separate, or clone the full repository.
Fernando, you want to make this a little bigger too?
Oh, let me see if I can. Yeah. Oh, yes. Nice catch. So we're going to start with the SAR and Dask for large-scale imaging part 1. You can use this if you want to exercise your typing skills. Otherwise, if you just want to follow that, you can open the solved version and just see the results of those cells. Here is going to prompt you to select the kernel for that notebook, so you can use the scaling up with Dask kernel.
There is one on that list that says Dask, but you want the scaling up with Dask. That other one is an older one from the past, so please make sure you select the scaling up kernel.
Yeah, thank you. So I'm going to close this. And here.
Is there anyone that isn't at either using Navari at this stage, where they have access to the notebooks and they've launched the kernel, or that they're running locally and have a kernel running? Is there anyone that doesn't have that yet? That still needs help with the setup? Great.
Yeah, oh, thank you.
And if anything keeps up, just let us know.
Yep. So before starting, I want to know how many of you are familiar with Dask. Yeah, okay, yeah. So for those who have not worked with Dask, it's going to be like some quick introduction, and for those who already have worked with this, is just a refresher. So the idea of Dask as package in Python is enable to use lazy computations of on data. I'm going to just briefly introduce what the Dask library is, but mainly because we're going to be working with images, we're going to be using the Dask array module. So Dask array implements some APIs to work with chunk data. As we saw before, it is quite efficient to store your image data in small chunks, and then you can get access to those only when you need to process or to compute on those. Dask array, what it does is basically open the full image lazily. So it is not moving that into RAM. It is just like creating something that is called a future, or could be thought that it is just waiting there for you to compute on the data that you are loading with Dask. But then when you actually are computing parts of the Dask array, it is converting that into an NumPy array, and that is where you can access that and operate as a usual NumPy array with any tools that you have already been working on. So we can start by just creating some Dask arrays. So for those who have never used this, I think it's going to just show you like some of the interface of Dask and how it's going to be shown in the notebooks. So you can familiarize a little. If you have already done this, you don't have to do that. So to work with Dask, we will need to import, of course, the Dask library. And as I mentioned, we are going to be working with images, so it would be nice to have the Dask array also import. And I'm going to import this as DA just for short, so we need to type less letters when we work with this library. I'm going to import NumPy again as NP. And this is what we need to start with. So the idea is, for example, here, create a 10 by 10 Dask array that is this specific data type, and then make that be chunked into 5 by 5 chunks. So to do this, I'm going to create a D1 variable that is going to be just a Dask array full of zeros. So I'm going to use the zeros function to tell this that I want this to be 10 by 10 with chunks of size 5 by 5. And the data type is going to be NumPy integer 16. Okay, so we can visualize what is there in the notebook if we just type this variable. And this is what I wanted to you to familiarize with. It is basically how to visualize the Dask array and how it is being treated. So you can have like this nice visual of what is happening and have a notion of what are actually being loaded into memory when working with this this object. So first of all, we have created this 10 by 10 array. We can see here that it is displaying this nice way the chunks that we have created. So those are the small blocks are those 5 by 5 chunks. It's going to tell us the data type, and especially with this, you can more or less know what is the actual size of this object on RAM. For this shape, you will have a 200 bytes object, and each of the chunks is going to be 50 bytes. And you could notice here that we have a Dask graph that is telling us how many chunks we have in this array, but also how many like graph layers of operations have been created until now. So you can manipulate this more or less like a normal NumPy array. So I'm going to access some of the elements. So create a slice, for example, for the first 5 columns and 5 rows, and assign there a value. So again, this has not yet computed anything. So this is just like creating this graph of operations that are going to be executed when we need to. So this is the part of that makes Dask lazy. So if you display what it's doing, you can see that the shape and the data type of the of this array has not changed, but what we see here is that we have created a new operation in the graph layer. So by adding this operation here, assigning to the slice of the array, we have added a new layer so to our graph. So when we compute that, it's going to go computing all those layers in that graph, and ultimately getting the result of as an NumPy array. Yeah. I'm going to show you this here. Well, basically what I mentioned here is this part. But then when we use the compute method of our Dask array, is when this computation happens. So this is now actually like triggering all the graph layers that we have integrated into this. So we have two graph layers. One is for creating the zeros array. One is for adding a value on that slice. And then we see here that this is now an NumPy array after we have computed that. So let's add more layers to that graph. A nice part is that most of the operations that you can do with NumPy arrays, you can do that also with Dask. So for example, doing this is just this broadcast operation that adds a value to the whole array. But then if we see here, we have added with this new layer into our graph. Yes?
Since you computed the first two layers, is it the case that when you add a layer and run compute again, it will preemptively like cache the results of the first two layers and only do the third layer, or does it redo the whole compute graph every single time?
Yeah, it will do the whole graph. There are probably some caching in between, but this is you should think that when you do the compute, it's going to run the whole pipeline of operations. There is a way to do some caching, and I'm going to show you that. But basically, you can think that when you do the compute, it's going to trigger all those operations every time. So even if we compute at some point that we do this other operation, we can see that this is still the number of layers in the graph that it has to perform.
And then I guess similarly, if you do d1 plus 1, like x equals d1 plus 1 and y equals d1 plus 2, you now have two ends of the graph which share a lot in common.
Yeah. So
if you call compute on both, it will still
it will run the graph on that.
Do you want to repeat that for the microphone?
Oh.
I think that's a really good important question.
Yeah. The question is, and I'm going to show that when we have the projector. But if you have seen that every operation that you perform is going to add a layer to the graph. So if in a part of the pipeline you end up with separating that into multiple variables, each of those objects are going to share the same graph. So if you want to compute on one, it is going to it has to go through the full graph when it is common when it was shared commonly. Yeah, so I think we can check that operation after this. But what I wanted to show you is that you can also know the shape of your chunks that you have in your array, because it is going to show you here graphically like the size is not actually giving a good insight of the actual size. You have here the shape of the chunks, but it could happen that if your array is bigger than the integer number of chunks that can allocate, you're going to have some chunks that are smaller. We're going to check these in one moment. And I think it's a good point where we can add the other idea. So I'm going to create here another array. This time is going to be filled of ones. It's again a 10 by 10 array with this time chunks of 3 by 3. So if we inspect the D2, the D2 object, we have this like uneven or not uniform chunks because you cannot split this 10 dimension in between three, the shape that we gave to the chunks, that is 3. So to have an insight of what is the actual size of each of those chunks, you can use the chunks method to inspect that. So it's going to tell you dimension by dimension or axis by axis what are the sizes of the chunks. So we have here, this is a square, so we have 3 rows in the first chunk, 3 in the second, 3 in the third, and then only 1 in the fourth. So this is some of the methods that you can like utilize to inspect what is happening in the intermediate steps. And it's going to be helpful, for example, if you do the 3 array that is the sum of D1 and D2. And we inspect what is inside, we can see that now we have a mess of the chunk sizes. Yes?
What does it mean it has 7 graph layers? It used to be 1 graph layer in the previous visualization for D2 and 1 graph layer in D1, but once you add these two, you get 7 graph layers when you inspect them.
Yeah, that's a very good question. There are some layers that are not necessarily added by us. So Dask is going to try to do some rechunking in some cases. So this, as we see, is not not even the 3 by 3 chunks or 5 by 5 chunks that we give to any of those. So there have to be some intermediate operations that are introduced by Dask to make this operation possible. So some of those operations are going to be added to the graph without us actually explicitly telling it. There are, for example, the data type conversion. If we use, because we created D2 without specifying the data type, it is by default the NumPy float 64 data type. So to add that to D1 that is integer 16, it must be a cast first. Then you can actually add those. So those are the operations that are added to the graph and will need to be applied.
Can you also see the graphs?
For that, this is tricky because you can quickly lose the track of because it is going to be a big graph in very quickly. So there are a tool that you have to install, like a viewer, to get access to the graph viewer. But as I mentioned, it is like not that. I would say like efficient to look at because you start to get too many layers that you lost track of the operations, and it is just going to be too big to fit in your monitor. So this is why I didn't add that to the tutorial because one, you have to add an additional package to the environment, and the other is that it's not going to be that helpful. Of course, if you go to the Dask documentation, it's going to show you like some nice graph of that. I think I have that already open somewhere. So there is like a package that you will need to install to get this visualization. But as I mentioned, as you start like creating like a lot of operations, this is going to grow, and this is not going to be very helpful. I think there is. I don't remember what is the package. If you try to actually, if I try to do this visualize, it's going to prompt you what is the package that you need.
And the method is .visualize. I think you just call it here, right?
Yeah, yeah. It's going to need graphic graph, bis, or IPyCitoscape. So you have to add any of those two packages, and it's going to allow you to use the visualize method. Yeah. It worked. So you probably have already some of those packages installed. Yeah, but as I mentioned, sometimes it's not going to be very helpful if you are like analyzing a very big pipeline. But yeah, it is a tool that is there already.
Thank you.
Yeah, absolutely. So we have seen there are like this idea of chunks that Dask managed by itself. But we can specify if we want to make this rechunking by our own. So for example, the D3, again, I'm going to display that. D3 has this uneven chunk distribution. If you check with the chunks, remember, you're going to see that it is first a chunk that is 3, then there is one that is 2, 1, 3, 1. So this is probably not that efficient, because if you think that later we're going to spread these computations into multiple workers, you will have bigger chunks for some workers, and then you're going to have smaller chunks for others. So the load is going to be unbalanced. So it is more or less advised to have like an uniform size of chunks. So you can do that, for example, in here, if you give this D3, I'll run this just here. So rechunk, and I want to force it to be 5 by 5. So notice that I haven't override the D3 object. I've just created like or launched this operation. So D3 is still this ugly chunk. But if you apply the rechunk, you will see that it's going to add another layer after computation of the previous layers. So it is helpful to like review where you will need to actually apply these rechunks operations. So, oops. If you have D3 is D1 plus D2, and then it would probably make sense if we rechunk D2 using the chunks distribution of D1. So what you have to check here is this is going to first rechunk D2 before applying the operation, and this has saved 2 operations in the graph. So because here we are adding this rechunking after operations, it will be saving us some operations if we do that before adding those. So because D1 and D2 in this step will be same chunks, so we don't have to rechunk something in the between. Again, like any other NumPy arrays, you can apply math operations. So I have here like some examples. Yeah. So I'm going to compute the sum of the 3. So MP sum of the 3. And let's check what it is. So this is also a NumPy, a Dask array that is still not computed until we explicitly call the compute operation or method of D3 sum. And we can see here the shape of the array and the chunks. It is basically 0-dimensional, so it is a scalar because it is reducing that into a single value with the sum operation. So if we want to get the actual value of this, we will need to use the compute method. And this is going to trigger all the graph and apply this final operation. So this is nice because Dask is not allowing it to compute. It is not going to call NumPy. NumPy is not going to force Dask to compute. So it's going to handle this in a way that it keeps everything in a Dask array until we apply that. There are some cases or some functions that force the computation. We're going to see some of those, and for those, we're going to use some ways that Dask give us to make, again, those computations to be lazy. Just to show you that you can apply other operations. You can apply, for example, the cosine function to the tree, and in this case, the result is going to be an array because it is applying that element-wise. But again, it's a Dask array until we compute that. Okay. So this is related to a question from before that if there are ways to create a cache between operations. So yes, this is the persist operation that we can perform. So this is going to partially compute the operations of the graph until the point that we are now. But this is going to keep this as a Dask array. So it's different from compute because compute is going to return you a NumPy array. Persist is going to return you a Dask array.
So you can still, it's still not actually executed, but whenever it does later down the line get executed, it will then reuse the graph up until that point.
No, this is going to trigger the execution, persist, and this in this moment. So it's going to run all the graph, move everything into memory, and have your Dask array as if it was a single operation or
so is this
graph.
just the convenience over, if I do d1.compute, and then I save that into a variable x, and then I call Dask from array x, what's the difference there?
That's because you have to add a new operation to create a Dask array from a NumPy array. This is keeping everything into Dask. Okay. There are some use cases. The idea is that you could apply the persist operation if you still have your array fits into memory, and you are going to apply other complex operations later. So the idea is probably persist is not always the best solution to do that. Yep.
I use typing d3.compute, and the array comes as 333 in 5 plus 5 chunks, and the rest of the chunks are 222. I was confused, what does that mean? So I was plotting each of the d1 plus d2 because they got summed up. But d1 was initialized before as zeros and with 111 in the chunk. But now when I print d1.compute, it comes out as the first 5 plus 5 chunk has 222, and then the rest has 112. And I haven't done anything with d1, but it somehow got modified.
Yeah, so it's is it still 10 by 10?
Yeah, it's still like I get your same answer. Like if you just type d3
Yep.
compute, you can see that it does not correspond to how d1 or d2 was initialized.
Yeah, I wonder if there is an additional step that probably was added somewhere there. So of course this is I will say the issue does.
D1 was modified, where we call d1 dot 5 like index.
Yeah, in the very beginning, right?
1, and then so everything should be 0. But if you type d1 dot compute now, right now you will see it has changed. You will get 222 instead of what we initialized d1.
But D1 was rechunked, right, in order to be able to do the addition. So
Yeah.
I think that the graph of D1 now has rechunking in its operation.
And that should, just the chunking version has
it can change the numbers of the chunks, of course, the size of the chunks, but the value,
Just,
this one.
D1.compute, you will see something else now.
So I wonder if it is probably related to,
Yeah, these operations are the same operations, but if you just on D1.compute right now, you will see that error got modified. This is not the error right now.
you can repeat what is the value that you get?
I get 222 in the first 5 plus 5,
I think.
and the rest has, yeah.
Is that, oh, yeah, sorry, yeah.
How did that get changed from that to this?
Yeah, I think that it is something that we will need to take into account. We are running, of course, this in Jupyter. So if you go back and run something again, you're going to probably mess with the order of operations. So what I think is that we should have to compute this before adding this addition. So if I run this again, it's going to be after whatever I have done, because I have messed with the order of operations in Jupyter Lab. So I would say that you can always run again from the beginning, and you will have again the same result. What I didn't do was computing after this, so I didn't apply this. But yeah, it's basically you apply the compute after this. And this is why you get that. It is just because you apply the compute after that. So this is what this idea of the graph layers is applying. As I mentioned, you can compute in any time, but it's going to give you the result at that time. If you continue adding other operations to the graph and you compute, it's going to give you the result after those operations were added. Yeah, it is like there are some order of operations that you have to take into consideration. Like as I mentioned, like when is good to rechunk, and when you are going to be using the persist, something that I was about to do. So let me define this variable again as this d2.rechunk 5 by 5. D3, just to show you again the number of operations that have been added to the graph. And if we do D3 equal to D3 persist, and we show what is D3, we are going to see that first it is still a Dask array, but then you see that now you don't have any other operations on the graph. It is like, this is the current state of D3. Okay. So we're going to start with the light operations, but before that, how much time? We have been here for like 1 hour. So it will probably take, what is good, 5 minutes break? Yeah, so we can come here at 2:40.
Yes.
I mean, yes, but no.
The images that you get when you put like the Dask array and then you show it on your notebook, do you know if there's a way or method to show that? Like I was running it in Spider or a different ID. Is there a way to like generate those images as like? Yeah, or like just showing them like you know, like a QT or a math problem. Like I guess if because it's useful to be able to see the array shape without having to like read the chunking or
Yeah, because of course, if you run this and just pure command line.
yeah, you're not gonna get any images.
Okay.
That's all you get, but it's like so I was using an IDE, but like it doesn't. Jupyter, I switched to Jupyter because Jupyter is well gives you
The visual of
the
this,
visuals
yeah.
and then
I really don't know what is generating the visual. If it is,
all good. No, I'm just curious.
Yeah.
I'm sure that there's something that's
Yeah.
generating it.
I think that I'm pretty sure that I remember seeing an extension, for example, for VS Code to show those. I think there's a Dask extension.
Okay, that would be useful.
But I think that it's basically using the Jupyter, like HTML style render.
Yeah, that's gonna be it.
So, but if you're using PyCharm or something like that, you might need to Google to see if a similar thing is available.
No, I'm using Spider.
Or yeah, well, whichever.
Yeah. But then if something could generate the HTML essentially.
Yeah, and then render. So I think Spider uses Qt console, and
Yeah.
IPython basically. So I think there is a widgets thing for IPython, and so I think it's like you have to Google like Dask IPython widgets or something in order to use it. But I know those things exist. I can't off the top of my head tell you how to do it.
No, I'm sure I can look it up. I was fine.
Yeah.
I was giving that for granted.
Yeah.
Yeah, that is definitely one nice thing about like Jupyter notebooks is that like that's an option.
It's very.
And in the Napari one, we leverage that same trick with this NV screenshot, and that also won't work in other environments. Like if you run in IPython, it doesn't work.
Yeah,
because it
they're one of
uses
the things
the-
like, okay, this is one of the niceties of having web attached.
Yeah.
Jupyter, yeah.
Yeah, exactly.
And no, I just like having, I don't know, my little .py file.
Right.
Can I ask, I don't know if I missed it, when we did the sum,
Uh-huh.
and then when you jumped to the like 3D, whatever it was, how does Dask decide on that chunk instead of like, why didn't it go to 5.5 if that was like, not obvious, or like, does it do any more, like, what's the logic?
Yeah, I don't know if it is related to trying to keep the size in bytes probably. I don't know if it is saturation stuff or if it is going to the minimum common.
It's going what, sorry?
Well, it's not doing the minimum, right? Because you would think it would finding the lowest common denominator would be the minimum. So they would reach, but then it would have to.
But there are ones in the right.
Yeah, like it didn't shift those like,
Uh,
yeah.
I think it is heuristic there because this is for 2D, but if you think that you can do that as for n-dimensional, it's going to do some weird.
I don't know that, especially what was displayed here. Like I can't imagine. I have a hard time imagining that at least for downstream. That might be the simplest way to add those two arrays together, but it's probably not ideal for downstream processing. So in those cases, if you have arrays with different chunks, it probably makes sense to re-chunk one to match the chunks of the other in order to basically bypass the logistics. But it must be doing something with just basically trying to make the minimum number of changes or something like that.
But it'll be deterministic, right?
Yes, I think so.
Yeah.
But it's clearly not just computing the lowest common denominator.
No.
Because then it would be 5, right? It would
Yeah.
just re-chunk both the 5,
Yeah.
add them, and be done. But it might be that it, for example, will not increase. So if you notice with the summation, the chunk size didn't go up.
Yeah.
So you always had 3, but then you had 2 and 1. So it could be that it won't re-chunk up in order to merge them, so it only chunks down in order to protect memory, right? Because then it's never going to load something that you would expect. So it might be that the algorithm literally works just like that, like
Yeah.
chunk down.
Yeah.
Yeah.
Okay, I think I'm going to continue with the explanation of Dask delay. This is a module that is inside Dask that allows us to convert a function, a Python function, into something that can be applied lazily and be still kept into this lazy state without having to compute intermediate parts of the graph. So this is like an example in the Dask documentation that is, you are basically creating these x and y variables from some initialization function that you can imagine that is probably quite expensive to compute. And this is why you would like to keep that as delayed as possible and just compute when necessary. And these are for mainly pure Dask computation. We are going to see that when we work with Dask arrays, we will need to do some conversion from the delayed version of operation into something that is, again, a Dask array. So the idea is that you can, this is like a toy example, but the idea is that your initialization function could be something like open a file from disk or compute some grid of values and apply some operation on that. And again, we don't want to spend too much time loading all those pieces into memory until it's ultimately necessary. Okay. So I'm going to show you probably what we want to achieve here and go back some steps. So to explain the implementation of this. So we want to create some Dask array that is somehow like operations that allows you to generate this grid of values. This is like a gradient in x axis, a gradient in y axis, and then we want to apply an operation on that. For those who have been working with R, this is something that you would apply using the outer operation. Probably not necessarily something that all of us have worked with, but you can think that you want to apply a certain function to each of those coordinates, but then you will need to create the coordinates grid first. So we are going to implement how to create the coordinates grid, and then use that with Dask array to lazily load that until it is necessary. So I'm going to start by typing something, and then I'm going to grab that to create a delayed version of what I'm mentioning. So we can think that we want an X, a big X array of values that is a gradient in the X direction. So something like an A range, probably starting from some offset and going to the offset plus the width of that grid. And then replicating that, this is just this one-dimensional array. We want to replicate that to create a two-dimensional array. So I'm going to use here tile to replicate this height number of times. So this is the operation that I would like to apply. Of course, you will be able to define some offset. For example, just start in 0, some height for some 500 pixels, and a width of other size 500 pixels. So to run this, and then just show you, of course, import matplotlib pyplot as plt to show you what x looks like. Plt im show x. So this like gradient array of values on the x axis. We could apply this to have an y direction. So in arrange from some offset, the offset plus the height of that, and replicate that. I think we need to do some trick here to treat this as a oops, come on, here. So just adding an additional axis to our array, so we can replicate that as columns. Otherwise, we are going to end up with some weird shaping of the array. And we're going to replicate this width of times. So again, run this. And this is for x. Plt im show y. This is for y. It is the same grid. And we want this for example, applying some operation like c equal x squared plus y square. Plt dot show c. So have this kind of gradient operation that is applied to that grid of values. So this is like probably a toy example, but of course you can think that if you are going to operate on a huge data array, you would like to prevent from doing this and loading the whole huge array on memory. So you would like to make this operation as lazy as possible. So I'm going to create this as a function. So I'm going to define grid x. We pass the height, the width, oops, and the offset. Probably the default as 0. So this is. Yeah. So you see here that I'm actually computing all those arrays. This is normal NumPy arrays. But if you think that I'm using just this small 500 by 500 arrays, if you think like you need to do something like this 5 million by 5 million, you don't want to create that huge array until it is ultimately necessary. So this is like a toy example, but you can think that here probably the is to give an example of operation that where loading the data is probably the heavy part of the pipeline. So this is what you would like to create as a delayed version. I mentioned that if you're, for example, loading image data, you don't want to, for example, load all your images. You want to, for example, apply a pipeline that is applying an operation on an image at a time. So you don't need to move all the images to memory. You can create a delayed version of that loading process and just load the images as you need those. So this is the concept of delayed or creating a delayed version of your function. So in this case, we are returning this gradient version of this array in the x direction. I need to do the same for y. So we have a height, width, and offset. Return y. So this is a normal Python function. So if you call that, you are going to create a NumPy array as we define here. So to make it lazy, and I'm going to probably just remove this, we're going to use Dask delayed decorator. So you add here at Dask.delayed. And with that decorator is going to convert your function, your Python function, in a delayed Dask function. Okay. So I'm going to define here, for example, big X, capital X as grid X, and give some values. Of course, if I could write or type it correctly, grid X. Okay, yeah, I mistyped that typo. So we check what X is. This is not computing the function. It is returning this delayed version of the function, but it is evaluated on these values that you pass to the function. We can do the same, for example, for a Y, capital Y is a grid Y 500 by 500, and again, it's a delayed version of that. But then if we want to do, for example, a capital Z X square plus Y square, oops. This is a nice part because this is still a delayed version of that operation. The issue is that, well, if we want to actually have access to the elements, if we want to show C, you cannot, you still don't have access to the values because it is still a delayed version of this sequence of operations. So you will need to convert this delayed version of the operations into a Dask array first. So I'm going to remove this because this. So I'm going to create this DA underscore X. That is our Dask version of the capital X variable. So I'm going to use Dask array and from delayed to convert this delayed function into an actual Dask array. So I'm going to pass this value, that is the delayed version of X. The tricky part is you need to know beforehand the size of that, of what is returning that function. So we know, because we defined that, it's a 500 by 500 elements array. And we know also that is of data type NumPy float 64 because it is just using the default data type of NumPy. And if we inspect this, this is a Dask array. So it is still lazy. It is still just defining it as a sequence of operations, but it has not called the function to create this. So we don't have this large array on memory yet until we perform the compute operation. So we can do the same with Y. So Dask array from delayed Y, and then we know that this is a 500 by 500 with type NumPy float 64. And then I can create a DAC, that is the operation that we wanted to apply. So X squared plus DAY squared. And DAC is, again, still a Dask array. And if we call plt imshow on DAC, this is going to trigger the computation and actually return the addition. So it is, by triggering the computation, it is calling the delayed version of the functions, converting those into Dask arrays, creating this, applying this square operation on each of them, and then adding those together to get the result. Something that you might notice here is that this is a single chunk. So the full image is a single chunk.
Would you have just done DA dot from delayed x squared plus y squared instead of first doing DA from delayed on x and then y?
I think so, because you only need to get here a delayed version. So yeah, you can like operate as the orders as you want. The only thing that you have to consider is, again, the size must be the same that you expect. So we're going to check what how you can take those Dask arrays and concatenate, stack, and create blocks of them. So I'm going to continue with this idea of this problem of creating this lazy version of a big grid where we can apply some operation on. So this is going to be probably a little silly, but I'm going to create Dask x00 array. And then I'm going to use, this is the other way of defining this, is from the lathe. So we can put here directly the function that is the lathe function. So in this case, grid x. We are going to call that function with these values. Oops. And of course, so this is what we want to pass to the Dask from the lathe. So we need to tell it the size of the array and the data type. So probably not going to show each of those, but this is the idea. It's the same. You can create that directly from a delayed function that is evaluated. I'm going to copy this multiple times because I want to create something that is like a big stack of these blocks and show you how you can like concatenate those together. So I'm going to create something that is, for example, one index to the right in the X grid. So instead of going from 0, this time it's going to start from 500. So it is like just continuation of this gradient version of that image. I'm going to create similarly capital Y 0 0 Dask array from the lathe grid Y 500 by 500 starting from 0. This 500 by 500. Data type is numpy float 64. And just going to copy this. Again, and then this is like one index, but in the y-axis. So the only thing that I have to modify here is the offset. Oops, 500. Okay. So we're going to use some operations from Dask array to put our arrays together. So we can like have an idea of what are the difference between those three operations. So I can use stack. So you're going to pass here a tuple of all the arrays that you want to stack. This should be like the same shape. So for example, if you would like to stack this x0 and this capital 0 and 1, and you assign this to stack in axis number 1, this is going to happen. So this is stacking those like one on top of the other. It is creating a new axis in the axis index 1. That is the second axis. And as you can see here, it's like you can see nicely that you have these two big chunks, but those are being stacked together in that orientation. So for what I wanted to make is probably not the best solution, so we can try better with concatenate. So again, pass their tuple, 0, 0, DA 0, 1. Oh, come on. And the axis is 1. So, yep, it looks closer to what I want to achieve. So now we have concatenate those in that axis. But the problem is that if you would like to create like a bigger square, you would need to like nest a lot of concatenation operations. So it's going to be not that efficient because then you're going to have to know beforehand this configuration that you are going to give this. So there is a third nice operation that is the block operation, and this is actually what I'm going to end up using. So DA block. What this receives is a list or a nested list of the Dask arrays that you want to put together. Similarly, as when you create a NumPy array from a list, the list format is going to tell what is the shape and the axis that you want to use to create this array. So for example, I'm going to use here the x0, 0. Oops. 0, 1. Close this list. And then add here a second row that is basically the same, because this is the doesn't change in the y-axis. And close the second list and directly show what it is doing. So this is achieving what I wanted to do. You can as well create here like a neat dimensional array by modifying the configuration of the lists. So this is how you could put together like multiple individual blocks into a big Dask array. So I'm going to probably just copy this and do the same with y. This is just for completeness. I'm going to change the names of the variables. In this case, this is changing the index here. So we have difference in the y-axis, but not difference in the x-axis. So now we have two big Dask arrays that are put together by smaller chunks. And you can imagine that you could continue doing that and create a very large Dask array. The nice part is that because it is from the lathe, it is not going to compute any of those small chunks until it is necessary. So now you will do the DAC from those new big arrays. Okay. Yep.
Is there some intuition around why DA underscore X has 6 layers, but DA underscore Y has 7?
Yeah, I think there is. What I think is that is probably in the Dask array function that I added there like a new axis. There is probably adding this additional operation because it is converting this function into a delayed version. So I would think that is that. Yeah, but again, I think that you will need to like go into the graph and look at the operations. I'm not sure if there is like a nice way to, again, like to visualize that so you can see what are the operations. Yes, for some debugging stuff, you can start with small, relatively small arrays and then moving again into bigger stuff. So what we do here. Okay. So just to finalize this part of Dask, I will introduce now how we are going to use Dask to work with images. So I have here this image that I would need to download. So this is an example image, but it is not actually right now here. So and the idea was to show you the magic of using TIFF file from this. So I'm thinking, what is the best way? It is just downloading that image is going to be probably the best way. So if you
using Navari is probably not going to be able to.
I think that there is a way. So if you go to the test images part of the installation instructions, you have that at hand. It is, again, not necessary. The second part is going to be using something that is pulled from cloud storage. So if you don't want to do this piece, it doesn't matter. It is just for showing you more like an example than an exercise. So if you go to the open slide, sorry. Is here the example repository of images. This Apereo SBS. You can find here the CMU1 SBS image file, and I think. Sorry.
Zoom in a little bit.
Yeah. Yeah. So this is almost 170 megabytes image. Bright field imaging. It is compressed using JPEG, so this is why it is not a huge amount of storage required for storing this, because it is compressed in using image compression, and it is CC0, so we can, I would say, safely download that and use it for this example. So I think if you copy the link address, it is the download address. I'm going to check that. So I'm going to download that directly here. So wget quotes, and the link to that, yeah, it's going to be already CMU-1. So what I'm doing is using the exclamation symbol to be able to execute bash commands in Jupyter Notebook. So we are using basically wget from bash to call that directly from this. So we don't have to download that and upload that again. And this is going to be stored directly on your notebooks directory where you are.
So it's just the kind of environments that are long. It's not the fact that we couldn't modify the images that we couldn't install. Good to know.
Yeah.
I assume that you can download into the container because
Probably,
we
yes.
with installing things into the container, but it turns out the container is just protected from installing.
From installing, yeah. Okay, so it's not going to take that much time also because this is running on the Google Cloud platform, so they probably have a better internet that we have in hotel rooms and whatever. So basically, because we have that image here, I'm going to import SAR and TIFF file libraries, and because it is already here, I'm going to change the input path to just point to it's just directly here, so input path, use this. So let me know if you are probably already here or if you have any issues with getting an image. But again, this is just to show you.
And if you're running locally, you could just download the file locally.
Yep, directly.
And then change the path from C
Yep.
blah, blah, blah to the path locally where you install it, where you download it. Yeah.
Do these SVS files auto-convert to TIFF? Like, it seems like it's doing that, okay. And they're intercompatible?
The wget doesn't. It saves it as an SBS.
No, it's an SBS, but an SBS is essentially a TIFF variant. And so TIFF file can read SVSs because it's a TIFF variant. There's a whole host of formats that are really just TIFFs that are tweaked a little bit. So SBS, there's CCI, there's
NDPI.
NDPI, there's a host of these different file types that are really just TIFFs. So TIFF file is a very powerful Python library for doing this. I would say it's the cream of the crop. If you're doing anything with these types of files, find a way to use TIFF file because it's the most performant. And it has this cool ZAR backend, which is very, very useful.
So just as Peter mentioned, I'm going to use this to open this file. So I'm going to create a variable that is a TIF store. You're going to know later why I'm calling that store. So I'm going to use the TIFF file. Those are 3 Fs. And not 4, not 2. I am read. So this is where you have to be careful with pressing enter because you have to pass here the input path. And before calling this, make sure that you are using the as_SAR argument equal true, because otherwise it's going to just read the image and move that into memory. So this is a 170 megabytes compressed, but if you open that, it's going to be use the NumPy array that is 5,000 by 5,000 pixels with 3 channels. And it is going to be, depending on the data type, it could be just integer 16 bytes, or if it is stored somehow as a float 64, it's going to be exploding on your memory. So if you're in this, this is just going to be, oh no way. Yeah.
It's the wrong version of SAR.
Yeah, and I think I know what could have happened there. It is not the version of SAR, it's the version of TIFF file. Let me just check here quickly. What can I do? Yeah. It is just that, or I have to do the... Yeah, right. Yeah.
Yeah, that's the latest version.
Yeah. There is a weird part of the installation instructions. I was testing with explicitly telling it the upper limit of this version to be less than this, strictly less than, and it anyways installed this version. So it's probably the people that set up the environment could have used have the same problem. The issue is that TIFF file, the most recent version, is just directly going and checking for your version of SAR, and if it is less than 3, it's just going to raise this value error. So you could probably still work with that, because this is probably not doing anything. It is just breaking because it is forced to look for SAR version 3. So if you could install, I think it is the 521 version, you will be able to work with SAR 2 still. So, well, I'm going to show you what I was planning to do with the solutions. So I'm happy that I have this pre-compute. Okay, so what this is going to do is return this TIFF file SAR TIFF store object that is like a pointer to your data. So it is again not loading anything into memory. It is just a pointer to where the data is located. So you can pass this to SAR. So SAR is the Python API for opening these next generation file formats, the SAR format. And then you can open this store in read mode. And then you have access to the pixels as if it was a SAR array. SAR arrays are very similar to Dask arrays if you think on the data that those are chunked and those are lazy. So this is only load into memory when you are calling a specific region of the array that you want to compute on. Basically, it would allow you to operate on this. This is a 32,000 by 46,000 pixel image with 3 channels. And just accessing it using this small 200 by 56 by 256 chunk sizes. So it is not going to open the full image into RAM. It could just extract small chunks and concatenate those into the region that you are operating on. So the idea is that Dask array that has also this from SAR function. So it is similar to this from the lathe or from NumPy. It's from array. So it is basically either pass the path to SAR file, or in this case, this store object that is returned by TIFF file. And then you can access the component that is basically the level inside the image. The image is what is called pyramid version. So it is downsampled. So in the level 0, you have the full resolution image. And the next level is going to have a downsampled version of that. And the next level is going to be an even more downsampled version. That is mostly used for visualization purposes. So if we want to operate on the full resolution image, you will access the component 0, that is the top level. And this is what I was telling you. If you load this into memory, it's going to be a 4 gigabyte array. But it is just loading this 192 kilobytes chunks at a time. So if you are operating on, for example, multiples of this, it could be like more efficient rechunking. So it's going to be loading from disk into memory multiples of those chunks, and you can operate on those safely. So there is, again, these rechunk operations that if you would like to have all the channels in the same chunk, there are some times that your image is split into channels. So a chunk contains the RGB, the red component, other chunk is going to contain the green component, or the blue component. So if you rechunk that, you will have the 3 components in the same chunk. And any operation that you apply, you're going to get access to the RGB image. And in this case, as I mentioned, because this is a multiple of the actual chunk size, you will probably have like quite a decent rechunking operation without too much graphs added, layers added to the graph. After that, again, you can like access just region of that. It's going to just pull whatever is needed. So instead of pulling the 4 gigabyte image, it's going to pull a 12 megabyte region of chunks. So on that, you will be able to just display that using Matplotlib. The example was to implement something that could work on that. Yep.
So if you just scroll,
Oh.
when you're actually displaying that image, since you never did like a resize operation, when it hits matplotlib, it does have to then hold the 4 gigabytes of memory now.
No, it is just this 12 megabytes because we cropped this.
Oh, prop. Oh,
Yeah,
sorry, I missed
yeah.
that.
Yeah, but yeah, as you mentioned, if you show the full array, it's going to move the 4 gigabytes on. And it's going to take forever to, or going to break Matplotlib because it cannot plot that 30,000 by 40,000 pixels image. But yes, if you are like analyzing regions on your image, you can think that you can just take crops of that. Are there any? The downsample operation. This is already coming from the microscope or the instrument. Well, it is an intermediate step where when the SBS file is generated, it is mostly probably that the acquisition software is creating those pyramids and creating those, storing those. So yeah, but if you don't have that, there are conversion tools that are going to convert the image into an open source format, and it's going to it can compute those pyramids for you. So that was this part, and the idea it would be that to operate on images in this way, you could, for example, think on operating or creating this color to gray operation that takes the RGB image and converts that into a gray image, and you could create this as a delayed version of that. So it could combine nicely with the Dask array that you have your image. So you can think that you can convert RGB images in chunks to gray images, and just call this this operation because it's delayed when needed. So probably we're going to probably jump into the actual operation of this because this was requiring to have access to the T file, or actually not. I think we can still change the image from where we are taking that. Yeah. What are we doing in time? I think it's been another hour almost. So I think that we can take another 5 minutes break and probably start from here again so we can again go back into some typing and coding. So just let's return at 3:30, and we can use probably the image that is in the cloud bucket.
Yeah, it's the same image.
It's the same image. So I'm going to use.
When I was exploring, I mean, I settled on Dask recently, but when I was exploring, the other option was Vips. Have you used that before?
What is it's again like
Yeah, it's an out-of-core image processing thing. It's written in like C or C++ or something, but there's a Py binding for it. I just settled on Dask because there's so much of the SciPy community that's using it that I figured I'd get more support. But
Yeah, so that's like it's I think it's a pretty long-running project that started, I think, even before Dask, perhaps. I think it's largely, it doesn't seem like it gets as much use broadly in the community as some of the more universal things. So like Dask is totally domain agnostic, right? Dask image is focused on images, but Dask is lazy and can be used with anything. It has data frame support. You can compute, data frames and things. So Dips is very much more specific, but I think that in terms of like performance implications, I think So it's not better or worse. I don't want to, like, I think it's just like a different,
Yeah.
you know.
Yeah, I mean, my whole thing was more if I need help.
Yeah, like, Dask does a wonderful, like, the Dask community is awesome, and there is a lot of help.
Yeah.
The other really cool thing about Dask, depending on what you're doing, and I know some of the things that you might be doing, is a thing called coiled. So coiled is basically like a Dask spin-off where you give coiled your cloud keys essentially, and they will create clusters for you dynamically as the demand. So
Right.
basically, you have a content environment on your laptop, and then coiled will package that environment, ship it to the cloud, distribute it over n number of instances, do computations, group everything back, and drop it back into your laptop.
Mhm.
It's pretty wild.
That is
But it's pretty powerful for cases where you have like organizational level cloud support, where you don't want your stuff leaking into somebody else's cloud because you have some permissions and privacy issues. So Coil can be pretty sweet for that. I would say that Coil would be like an alternative to having a cluster. Like if you don't have access to a cluster, Coil can give you basically the equivalent using your cloud, not proprietary.
right. Yeah.
So that's pretty cool. So if you're already using the Dask ecosystem and then want to scale up into this, essentially, infinitely into the cloud, then Coil is plug and play with Dask. With some of the other things, it can be a little trickier. But now there's so many different software as a service type of things that do this cloud compute stuff that there's more options. But I think Coil is one of the first ones that really pushed it. And it's not it's pretty fast because it's not just relying on containers. They're basically just running bare metal VMs in the cloud and pushing your environment directly to the cloud. I'm not paid or anything.
Yeah,
I just think it's a good product, and it scratches a specific itch in that it makes it very easy to scale up and run something from your laptop into the cloud and then back. Whereas otherwise, sometimes it can be a lot more difficult to do that yourself. Like certainly you can just go into log into GCP console and set up a cluster for yourself and get the compute. But with Dask and Coil, you can make it happen with very little additional overhead. And it can even be dynamic. So like you can, as the computations pile up, you can get more nodes and then it can prune them back. So you're pretty efficient with your stuff. So I used the install from the thing, and I got the right TIFF file using the Conda environment on my laptop.
Ah,
But,
yeah,
but I guess the Navari has the wrong TIFF file, and
Yeah.
so there's the issue. But then, then I would say, but then just use it the other way, because there's the different API. But then you've got the wrong czar, so
Different czar.
you're flipped this way now, rather than being flipped the other way.
See that?
It's so infuriating that there's this bifurcation where it's like the ground just.
So I drop in the in the channel, in the Slack channel, an URL that we can use to get access to an image. I think it is a crop of this image, but the results are going to be the same. And it is for we're going to get anyways just a small region of that. So we are going to probably just change the coordinates on some of the exercises. But for those that already can work with the local image, you can continue with that. This is for the people that are using Navari. So I'm going to go slightly down here. And yeah, so instead of using the local image, we're going to use already SAR converted image that we have put already on the cloud in a cloud bucket. So to access that, I would probably recommend using this an input path, and it's going to use this one. I know if everyone has access to the channel, the Slack channel. So you can copy that easily. Yeah, so you don't have to type this. So, did it disconnected?
Yeah,
Ah. Setting up with disk. I think I'm going to need to
At least do the
import.
inputs, right?
Yeah, this one and of course at the top, Dask. Okay. So rewinding a little, you can open Dask arrays from SAR images or SAR files using the Dask array function from SAR. So I'm going to call this DAR, so, sorry, R for array, whatever you want to call this. This is going to be from SAR, and then you are going to give here the input path, and you need to give the component that I think is going to be 0/0. The component is in the SAR file format. It is storing. It is basically like a folder of folders. So the component is telling you in what folder you should look for your data. In this case, some of the images, when you convert those contain other images related to that. So, for example, they have like a picture of the slice that was scanned, other images related. So sometimes when you convert that, it's going to convert those also, and those are going to be in this case like component 1, component 2, component 3. So sometimes, or I would say that most of the times, your image data is actually on component 0, and then slash is to directing that to go into another level in the SAR file, and this is the pyramid level that you want to access. So if we check what does it look like, this is a crop version of the original image, so it is not this 4 GB, it is only it's a quarter of that, it's a gigabyte image. When we converted that, we used chunks of size 1K by 1K. So the only issue that you could see here is that, again, like your color channels are in different chunks. We're going to see later that it's going to matter where you have, how is your chunk actually like formatted. Because for some computations on Dask, they apply computations on chunks. So if you're trying to think that your chunk is a color image, but you are giving it a single channel, there's going to be some issues there. We're going to see that in the next part. But for now, we can operate it on this image.
You may notice that there's also 2 single
Yeah.
dimensions, and that's because it's in the OME metadata standard, where you always have a T dimension, a Z dimension, a channels dimension, and X and Y. So because of that, it has those 2 singletons. It doesn't actually have any time or Z dimension.
Yeah, and then there is a third part. It is related to what Peter mentioned, is that now the color axis is in the front. If you open the image file, I think it is in the trailing axis. In this case, it's moved to the first part. But we can solve some kind of those issues. For example, I'm going to first get rid of those 2 additional axes. So I'm going to reassign this as like evaluating those 2 of those axes. So I want all the channels, but I want to get rid of these 2 axes.
I think there's a squeeze method that actually does the same.
Oh, yeah, that's true. But well, I would say that yeah. That's true. Yeah, that's true. There is there is now the problem that we have the color channels in the front. So I would say that we can use. Now we're going to be more smarter. So I'm going to use move axis from NumPy axis and apply this to our Dask array. We're going to move the first axis to the last position. So yeah, now we have the color channel at the last position. But now we have the issue that our image, the channels are in different chunks.
The question earlier about why do you do something delayed, I think this is a really good
Yep.
example. All of this data is in the cloud. And we haven't downloaded any data, but are able to reorganize the shape of the array and the chunks without actually committing it to pulling anything. And then once we're going to visualize or compute, then actually the data will start streaming in. But you can lay out it's basically like laying out all your calculations in advance, lazy, so you're not doing anything, but the plan is set. And then when you execute the plan, that's when the engine will start to turn. So it's really, really powerful when you're interacting with something where there can be big latency from getting the data to your computer.
Yep. So we're going to continue. Yep.
Could you scroll up just a bit?
Sorry, yeah.
Okay.
So I think that
All right, thank you.
that would be the operations.
Sorry, what was the resolution for the ZAR amplified version issue?
Sorry,
What was the resolution for the PIN5 and ZAR
Uh,
version issue? Because they just
oh yeah, there is. If you check the website with the Firser GitHub.io website, I'm going to put that here. Come on. So you go to the website that you can link from there. There are the notebooks. You have the empty notebooks and the solved notebooks. So this is the first part. So you can find that here.
Maybe scroll up and show the ZAR link from the cloud in case people missed that.
Oh yes.
That now you're loading data from a ZAR file that was already prepared.
Yeah.
Rather than loading it from that tick.
Yeah, it is just here. And you can find, I put that in the Slack channel, so you don't have to type that. Yeah, so I think that nice part of doing this conversion into SAR format is that you can store that in a cloud bucket, and each of those small chunks are going to be independent objects. So again, thinking on costs, if you want to access to just a specific region of your image, you only have to pull and download those chunks without having to pull the full image. And this is going to save some money on egress operations. If you are doing that in different cloud environments or locally on cloud. So I'm going to continue here. So some of those operations were because we're, instead of using the TIFF file or the SBS file, we are using this from cloud. But now I'm going to do this part of rechunking. So I'm going to rechunk. You can use the as a method. So rechunk this. I think this is still a good size. So I'm going to keep this size from the image files and just telling it that we want to have the color channels in the same chunk. So basically, this is the difference that our chunk is now an actual small tile image. So I'm going to go back here. looking at my notes, and yes. So the idea is, of course, not operate on the full image. So we're going to take like a selection of that. So I'm going to call this differently. So it's a cell from our array. And we can take like some crop of that. I'm thinking on probably just having some multiple of the, 24. Some multiple of the chunks, so we end up pulling some full chunks without having to do some partial chunks pulling. So probably going from here is just the second chunk, 24 times 2 plus 1024. So probably better ways to compute that. But basically giving control to where, like if we think like now thinking on chunks, instead of moving in the natural coordinate system of element by element, we would be moving on the chunk coordinate system. So 1024 times, 1024 times 3 plus 1024. Yeah. So again, because we took multiple of the size of the chunks, we are pulling actually a single chunk from there. Is there a question? Back? Okay. Where is it? Here is it. So there is where I'm going to follow some example, and then I'm going to let you implement your own solution for the next exercise. But the idea is to create a function that can be applied lazily to convert this RGB image into a gray image. So I'm going to import from scikit-image the color module RGB to gray function and create a Dask delayed function that applies this. So call it color to gray. What it receives is a chunk, so image chunk, and it's going to return this function RGB to gray applied to our image chunk. So we want to apply that to this selection. So I'm going to call this DA gray. So we need this from the lathe. Apply this color to gray function to our selection. And we know that the shape of this is going to be the shape of the selection minus the color channel, because we are compressing those three channels into a single channel. So it is squeezing that, and the data type is the same data type, I guess, that the original selection has. So we are like trying to reuse some of the information that we know with having to hard code the actual size of the chunk. So this DA gray is going to be a lazy operation applied to the selection that is going to return something that is now just a single channel image, and is preserving the size of that. And to show you that this is working, we can use plt show. I'm probably going to need to import this again. Import matplotlib by plot. PT. DA gray. Yeah, I probably took a white, an empty space there. So I would probably just select. Yeah, but chunk. What this is doing is, I'm going to probably give here and.
See a little bit in the corner.
Oh yes.
Some dust or something in the corner there.
So I'm going to use the color map gray to make it actually. Yeah, well, there is something. Yeah. So probably if you choose like a chunk to the right or a chunk to the lower, you're going to get more tissue there. Good point just to do that to show it better the result. So I took this selection from here. It's probably one below that. I'm running the selection again. I don't have to run this because we have already created that function, but we need to rerun this because it is applying to the Dask selection. And I think that this is also a nice part to point out is that we are applying, this is a delayed function, so we can apply that to Dask arrays. And it's not complaining about that because it is somehow knowing that this is in a graph, and then if you apply the light function, it is also in the graph. So it can be applied to any of this, I think either an NumPy array, depending on the operations that you apply here, but you are passing their Dask array and is anyways accepting that. Yeah, so this is a little more informative. So this is just applying this core map function. So I have an exercise for you, but I would like to know how familiar are you with image processing, like applying filters, like Gaussian filter, and applying thresholding operations? I think that I can show you the demo that would be just how you can extend this and apply multiple operations, because then I would like to actually spend time on the deep learning part of this tutorial. So I'm going to show you what the exercise was intended for. What happened to me? Did I? Oh, something happening here. I lost the extended version. Sorry about that. So the idea would be like an exercise of image analysis. A common pipeline would be to take an image, apply some thresholding algorithm to discriminate between objects that have a certain intensity in the pixels. So that would require to first convert your image into from RGB color image into gray scale. You can reduce the noise in your image by applying a Gaussian filter, and then you will apply some thresholding operation to discriminate between those structures based on the intensity of your pixels. So you can think that, going back here, there are like these dark objects here. Those are nuclei of cells in this tissue image. So those are darker than the background. So you could apply like a very naive image processing pipeline to discriminate those from the background. And that would require this set of operations. The idea is that you could think that you can apply this pipeline to a whole image if you break that into this set of operations that are applied to each chunk individually. So going back to this, the idea would be the same, is take your selection or crop from your Dask array, define the delayed version of your gray to color to gray function, and similarly define something that is a Gaussian filter.
My question is that, like, if you're using a model, not like Cyto3, but any PyTorch or TensorFlow deep learning architecture, and you load the model, will the Dask delay operation work using those PyTorch or TensorFlow-based models?
Yeah, it is independent from that because Dask is at a certain point is going to just send that to the function. We're going to see that probably in the next part. Yeah, the idea is that Dask is just managing how you access your pixels in the array. You can think of any element, and then all the operations like here are managed by other functions like scikit-image. Or there is this implementation of Dask image that re-implemented some operations from, I think this directly from scikit-image. So there are filters and other set of operations that have been converted to be able to work with Dask arrays. So you can apply those directly and just continue creating this graph of operations that can be applied lazily. The challenge here would be to define some thresholding method that could take your chunk and then apply something that usually is not defined in the Dask image. So that would require to apply this lazily. For that, it would be using a multi-Atsu thresholding method that basically takes your grayscale image and then computes multiple threshold levels that could separate the levels of intensity in that image. So in this case, it's going to return 3 levels of thresholdings. Your nuclei is the darkest intensity objects in your chunks. So you could take the first class and assign that as the nuclei object. So this is at the end just applying this conditional. If your intensity in certain pixel is below this level, assign it is a true. Assign it a true. Otherwise, it's false. So you end up with a binary image mask out from here. So this is something that you will take into account again when using from delay, because now you will have a change of data type that you will need to consider, because now this function is returning a Boolean data type, and otherwise it's probably going to work, but it is going to, if you use anything that is using more memory, data type that is larger than that, is probably going to create some buffers that use more memory than is needed. Sometimes it can break because if you are using a different data type that is not compatible with the casting. So this is just to, if you are like manually defining these functions, it is something that you will need to take into account. So after that, you will be able to show your image and overlay on top the output that you would require obtaining from that. So this will be the result of applying this naive thresholding method for detecting nuclei. But then let's take a jump into the more interesting part that is actually using deep learning methods and actually taking now the idea of using other backends that Dask support, like the distributed capabilities. So for now, we have been running everything on our CPUs as if it was a single worker that is applying all the operations. We can see that Dask is able to create cluster of workers that can distribute those operations. So we can see the graphs here that those are operations that are applied in a single chunk. With this distribution or distributed capability, you will send different chunks to different workers, and each worker is going to apply this graph of operations. Yep.
One last question about this. Is there, what's the intuition for using Dask.from delayed on the delayed thresholding method versus Dask.mapBlocks?
The map blocks?
Yeah.
We are going to see that, but
Okay.
the thing is that delayed is applying that to all the Dask array that you send.
Isn't that what mapBlocks does?
And mapblocks is going to apply that to each of the individual blocks. This is something that we have been working here with relatively small arrays. So you might not notice that we are passing, when you are calling the delayed function, it is passing the full Dask array to that. The mapblocks is going to.
Then why does the thresholding function have image chunk as the argument?
Oh, that is because there are not intermediate chunking happening there. It is, again, like the whole operation is applied on that. So let me. They probably didn't like took like a better. Yeah, I think that this is a good way to visualize that. So you have here a region that is composed by multiple chunks that are pulled from the SAR file. And then when you pass that through the delayed function, it's just going to create a single block for that. So the delayed function is probably not that intended for applying to array data that is big. It is like general purposes. You can use that for data frames or to do other analysis. So this is why mapblocks is better in this case of using that.
So with the delay, when you call .compute, by the time it hits the skimage threshold multi-OTSU function, is it getting the entire in-memory array?
Yeah. Yeah, that is like, so if you would like to apply this in block-wise, you will need to do this block operation that we did, to break that into blocks, put that together, stitch that together. So mapblocks does everything that for you. And this is what we are going to actually use. And I think we can jump into that directly because there is a intermediate step of using delayed. I wanted to show you the delayed function because it is something that you can implement functions that can fit in the graph, and that probably is going to be useful for some cases, but there are other cases that it is just necessary to apply the matblocks that just distribute the work across all the workers. So I'm going to put this back to me. So we're going to change into the second part. This is the notebooks, the part 2, and again select the scaling up with Dask kernel. So this is again like when you are taking that, when you're taking these materials home and you're reviewing that later, what we do to convert this crop of the image that we saved to create this SAR file was using this bioformats to raw function. So there's a link there to the project that is basically this open microscopy environment project that developed converters that can take a wide variety of proprietary file formats and convert those into the SAR format. Yeah, have a question? Yep.
I'm getting error. It says no worker found
This.
for Dask distributed get worker.
Oh, okay. Yeah. Yeah.
Which, you started the second notebook?
Yeah, I'm and I install the distributed over here. Restart the session.
Okay.
So you're running local.
It's full.
Oh, you're running it full.
So the other part here is that if you're running this locally, you can install the Dask extension for Jupyter that allows you to spin clusters automatically for you. And it has like a good integration with the dashboard that you can access directly from your session in Jupyter. We are not going to use this in Navari because we were testing this, and apparently they installed the extension on the base environment, which is different from the scale-up with Dask environment, so it is not compatible. So we are going to use a different approach here to create this local cluster that we can start here. So this is... So from distributed,
Quick question.
Yep.
Can you, like, quickly discuss what's the difference between the OME TIFF versus, like, the regular TIFF file?
yeah. So the OME format is like a specification that it has like it must contain specific metadata information for your image to make it like an actual OME TIFF file. Otherwise, you can just store an image in the TIFF format without any metadata. This is just going to make it a regular image file. But then the idea is that if you want to get access to the information that where that image comes from or what does it contains, it is very helpful to have this metadata information. So this is an effort from the bioimage community to have like something that you can share with people, and they can still at least know where that image comes from, or what specimen is that, or from where that image was taken from, the modality, the instrument that was used to acquire that image. So this is what makes the difference between the TIFF and the OME TIFF. And this is the similar part with SAR, because SAR is a file format that you can just dump arrays into this SAR format, and you can open that and operate that using the Python API. But to make it an actual OME SAR is adding their metadata that allows you to know what is actually there inside, at least what are the parameter levels, and if there are some scaling operations that you would apply to that. So it is like giving more metadata makes it actually an OME format.
So technically, you can convert an OME to a regular TIFF, but not convert it back.
Yeah. Yeah, so this bioformats to raw is most of the cases taking your file and populating those metadata. So this is where you get an OME SAR from that conversion.
It's particularly useful if you have like a proprietary format. So bioformats to raw will convert NVIDIA, the Zeiss format, the Leica format, with the help of the industry proprietary formats and sometimes by reverse engineering the conversions to be able to give you access to these.
Okay. So we're going to start by creating a distributed cluster in Bari. To do that, we are going to import from the distributed package the local cluster class. So we can create a cluster just by calling this, instantiating this class. So we're going to probably get this warning because it is by default using some ports that might be already on use. So it is just telling you that instead of using the usual 8787 port for the dashboard, it's going to then host it in a different dashboard, in different port. So then in order to actually use that cluster for computations within our session, we will need to create a client that is just calling the cluster.getClient function. And then if you inspect what is this client object, it has this nice, again, display of what is actually happening. So this cluster is running in the background of your computer. By default, it's trying to take as many workers as processors in your system you have, and then it's going to allocate the memory that you have available across all those workers. So if we expand this, we have a scheduler. The scheduler is what is actually taking those instructions that we gave to Dask when we compute, and then this scatters that to the workers to compute. And if we expand the workers tree, we see that we have 4 cores in this machine, so we have 4 workers, and then it assigned a single thread for each of the workers. This is the kind of configuration that you could manage differently. If you have multiple threads in a core, you can set that here. If you want to limit the amount of memory that you want to allocate across the workers, that is something that you can do also there in the local cluster instantiation. But the important part here is that we can get the dashboard and display that. There is a trick here to actually, for those that are working this, running this on Nebari, is that if you try to access this, it's not going to work because it is the local host in the instance that is running on cloud. So to make this work, you can open the Dask extension. I'm not sure, are you getting this already populated, some of you? But otherwise, I'm going to remove that. And I'm going to go to this URL from where it is running. I'm going to copy everything up to here, where it says your username. I'm going to copy this, paste this here, then /proxy, I'm going to add here the port of the dashboard. So it is 4073 /status. And then we have access to the dashboard from the Dask extension.
Where did you get the URL for the first part? Oh.
It is here in your, it is SciPy Quansi dev user, then the username that you use to log in into this.
Yeah, so it's the Navari URL, the one that you're actually connected to. So the Navari instance that you're connected to, that's the URL that you need to access the dashboard. If you're running locally, you can click the local host, the 127, and it'll work. Because locally it's running on your machine. But you can't use the local host if you're on the Navari instance, because it's actually in the cloud. 27, blah, blah, blah.
Yeah, you have to like expand some of this.
Yeah, you can just copy. You can open it in another browser tab, or you can.
Yeah, that is the other thing, that you can copy this and open that in a browser tab. And it's going to show you the dashboard again.
Yeah, so you can have it in your own
Yeah.
browser tab, or you can have it in Jupyter, depending on how many monitors you have
Yeah.
and how you're set up. That could be advantages or disadvantages of both.
So here, for example, you can add the task stream as a tab. So it's going to show here how your tasks are being computed across the workers. When we actually trigger some computation, we have the workers tab that is showing you the utilization of the CPU on each of them and how much memory is each of them using. What I think is not going to work is a GPU memory utilization, because we have GPUs on this machine, but we created the local cluster without giving that much insight of what is our environment respect with the GPU. But for do that, because we only have a single GPU, I think that you can use this extension that they have installed, and you can check monitor the utilization of your GPU. This is, I don't know what extension is this, but it is installed in the Bari environment. If you are more like rudimentary like me, you can open a terminal in the launcher and then use watch -n number of seconds NVIDIA-SMI and get your status of your GPU.
That's if you have an NVIDIA GPU.
Yeah.
If you don't have an NVIDIA GPU, that won't work.
Yeah. So let's go back to the notebook. So we now have a client. The difference with having a client defined in our session is that everything that we do with Dask is going to be sent to that client for computation. We don't have to specify anything afterwards. So we're going to see that I'm not going to specify what client we want to use. It is going to use as by default the one that we have called here. There are other ways to configure that, but it's like if you have like multiple clusters and you want to manage more complex operations that way. If you use the Dask extension, you can like get that a little easier because it is going to spin the cluster for you and it's going to give you like injection of the code to use this. So the next part is going to be importing the libraries that we need. So we're going to be using SAR, Dask, Array, Matplotlib, scikit-image. And we're going to be using the image from the SAR, the one that we have stored in the cloud. Or if you're running that locally and you can either download that, but you can use that even if you're running that locally, because it is anyways accessing that through the internet. So a little of inspection of what we have here is I'm going to create a SAR GRP. This is a SAR group. I'm going to open, using SAR open, this input path. And inspect what is inside this. So this is a hierarchy group SAR. If you use the info member, it's going to give like a nicer visualization of this. So what it's telling you is that it at least has a one group inside. So this is what I was mentioning, that you could have an image, and then inside that image you have multiple sub-images. So sorry, an image file can have multiple images stored inside, and there is where you have to point to what of those images you want to analyze.
But in this specific case, this then have to manually inspect the
Yep,
the
yep.
levels. So
So,
don't be concerned that you think that it doesn't work. It's
Yep,
actually
yep.
the data is there.
yeah, what I wanted just to show you is that if you go, as Peter mentioned, if you know what is the structure of your image, you can crawl inside and then actually get the info. Because this is, the SAR format is all these chunks. I need to show you how it looks like in my computer. So that crop image in my computer looks like this. So I'm going to go up. So is this OMSR file that is just a folder. If you go inside, there are like some, for SAR version 2, there are like some files that are point names. So in Linux, I think those are hidden, but then in Windows, you can see those. Those are like what actually tells you what is inside this file. So if I go inside this, this is the pyramid version that I mentioned. So there is the 0 level, 1 level, 2 levels, and metadata that tells us what is inside this level of the SAR file. And if you go further, this is how is actually the SAR file storing. So those are small chunks. So these chunks are what I mentioned is like very small tile. It probably contains only a single channel of the color channels. And we have this .CRA file that if you open that is basically telling you it open in the correct. So it is telling you what is actually this image looks like. So that way SAR knows how to put that together again. Without having to like crawl through all the files to know what is the size of the file. So this is what is stored in the bucket, and when you access that from using sar.open, it's going to pull that information from those metadata files. So. Before jumping into this example, just again, we are going to use Dask to compute lazily. So it would be nice to use then instead the SAR file, use Dask. So from SAR, input path, the component, we know beforehand it is 0 and 0, and again, is this gigabyte file that lives there in the cloud. We don't have to pull that gigabyte into RAM. It is just lazily living there until we compute on that. So similarly, as I from before, I'm going to use rechunking and selection of the axes that we actually want to use. So I'm going to define this as a selection of the 0 index in this axis, take all color channels, 0 axis, 0 index in that other axis, and whatever is the rest. Of course, we can use the squeeze operation, but I'm going to put there an additional rechunk in a single command line. Chunk. So 3, and probably preserving the size of this. Probably we could go lower. So for those that are not using a GPU, it's not going to take that much time to analyze the image, because this is going to actually be the scale of the image that we're going to pass to the GPU to perform the inference. So depending on the capabilities that you have, you can increase the size of this. Of course, this is going to go through your GPU. So now you have this you have to take into account how much memory you have in a GPU that is going to be shared, its memory across workers and this kind of stuff. So just to make sure that the operations make sense, we still have this trailing axis channel. So I'm going to move that with NumPy move axis or Dask array. We're going to move that from the 0 index to the last index. And now we are done. So now we have access to chunks that are nice tiles with all the color channels inside. And there is like most of the packages that work with images like tend to have this, expect this order of channels have to be Y, X axis, and then the color channel. So instead of computing on this, I'm going to take just a selection as an example. So from our array, I'm going to take, and I know because I have done this before, that if you go to coordinate 8,000 and take, for example, 512 slice and go to coordinate 2,000 in x-axis, and again take a 512 slice, you have actually something there inside. So just to show you that because these coordinates are not multiple of the chunk sizes of the original image, it is taking small pieces of the other adjacent chunks. In the under the hood is actually having to download those chunks because it has to access those pixels anyway. So it is probably, when computing this, you would probably see like a little overhead because it has to pull extra chunks. Then this is something that we are going to solve with using the map blocks. Yeah.
So the ZAR is chunked naturally, like at the disk level in 1024 by 1024 tiles, and then in Dask you rechunk it to 512 by 512. So then when it eventually calls compute or whatever, it will get a 1024 by 1024 tile over the network, and then split that into 512 by 512 subparts and process them. Gotcha.
Yeah, and that is probably going to be cached. So you are going to probably save some time because you are pulling anyways this 1024 by 1024, and it is now where you are splitting that to different workers.
So you don't always have to align it with whatever chunk size is native to the ZAR. You can rechunk it.
Yeah, and this. Yeah, and it is because sometimes your computation are going to be limited because of the requirements of your computer, and sometimes the store image is going to be optimized for storing that. So probably because of the costs, it is better to have some weird chunking. So you will probably have to do either some rechunking or think on that in these intermediate steps that you're going to apply. So this is where we actually start using our GPUs, and this is by defining the model that we're going to apply to these individual chunks. So I'm going to import from Cellpose models and transforms because there are some additional transforms that we need to apply to our chunks to pass to our model. Otherwise, the model is probably going to have weird results because when it was trained, it is expecting to have some transformations applied to that input. Otherwise, it's going to just create some unexpected results. And I'm going to import Torch just to have access to the CUDA is available to know if we actually have a GPU. And this is thanks to Peter to check that. If you're using a Mac with is GPU again okay, the metals. You will need to use this because otherwise, because you don't have an NVIDIA card, this is going to be false even if you have graphics accelerations. So this is used to take like your code and be portable across platforms. We are going to define the Silo tree model that is good for like general purpose segmentation of round, nice objects like nuclei in our case. And this is basically creating the model that we can apply. So we have to pass here that we want to move that model into the GPU and the model type. So inside this function, it is actually moving creating the model with PyTorch backend and moving that to your graphical unit, processing unit. So we can check what this looks like. Cell pose model. So this is a model, and how it is structured is that it is a class that it is an instantiation of a class that you need to use an evaluation method to perform inference. So let me show you how to do that with Cellpose. So we need first to do some transformations or apply some transforms to our image. So imgt is transforms. This is the library that we pulled from Cellpose. We have this convert image function, and we're going to use this now directly on computing our selection. So our selection, we need to convert that into a NumPy array with compute. We need to tell it where is the channel axis in that array. It is the second axis, the second index in the axis, so 0, 1, 2. And there is, we need to tell it that this is an RGB image, so there are no specific channels for different objects that have been stained for. So we can just tell that use the 0, 0 channels. Commonly, if you have actual staining of different objects and those live in different channels, you can specify that. This is a Cellpose thing. So this is converting that into a closer input that is required by Cellpose, but we still need to do some normalization step. So from transforms, we have normalize image img, and we apply that to our transform array. This is a NumPy array now. It has this invert set to false, and again tell it where is our channel axis. It is in the second index 2, the third axis. And now is when we can evaluate the model on our image. So this is generating the labels from an image. There is other stuff that we don't need. And we call our model, so pose model. And we use this eval method. So imgt. Other thing is that it is expecting a list of images. So we can trick it to think that our single image is a list of just a single image. So we add here a dummy axis. And diameter set to none, so I think it computes it automatically. Flow threshold equals none. And we're almost there. Where is my point? It's here. And channels again, 0, 0. And if we run this, this is actually moving the image to our GPU and computing the labels from that. I think if we see our utilization, we are going to see that the model plus anything that was like some catches happening when computing the inference are 824 megabytes. And it was quite fast, so we couldn't catch the percentage of utilization of the GPU, but if we run this with multiple images, we could probably see here how much computation is actually happening in our GPU. So we're going to go back here. And I think we can show the result of this just to have a grasp of what is happening. So PLT, I am show DS, the selection Dask array that we have, and then we are going to like overlay on top the segmentation that we got. So I am show. I'm going to use from scikit image the color module label to RGB. And I'm going to pass the labels that were generated as the inference evaluation of our model, and give it an alpha of 0.5, so we can see the both images in the same display. So this is what it is doing. So it is applying the segmentation. It is looking for objects that looks like the objects that were used when training the model. So it is actually like not only segmenting those nuclei, but it's more likely like segmenting like the cell. So we can see that there is a little more segmentation around the nuclei. And this is also, this evaluation step is applying some post-processing. Something that I mentioned before is that there are probably some operations that are applied after our image comes back from our GPU that still happens in the CPU. So those are additional operations that are applied by models, and this is like implementation details of each of the different models. So this is potentially what is now the bottleneck. Probably our GPU is quite fast to process the model layers of the network, but then it is this post-processing that could probably take some time. I think that I would like to probably skip this version of the late version of this, and it would be probably more useful to show you how to apply the matblocks operations with this. So we can actually define this as a function that can be scattered. I'm looking at the time, and it's probably time for a short break. So I think that 5 minutes is going to be 4:45. What is
the region props failed to like converge or gather. So you may consider skipping maybe the region props because it tried multiple times. And I had to kill the kernel in order to restart.
Yeah.
So you may consider the region, the full calculation region props. Like the other region props works. Like
Yeah.
the short, this works.
Okay. Yeah, because it is applying the
And then this
sequence,
works too. All this, the downsampling,
Yeah,
this all
the
works,
next
but the
part.
region props doesn't, and I don't understand this error message. So it says that it cannot finalize. Sorry. Yeah, it's having issue gathering the results back, I guess. Can't gather one key, rescheduling, and then it runs it again, and then again.
Oh, yeah.
And so it's something about like a retry.
Oh, it's timing out and stuff like that.
Yeah, so it's,
Okay.
I think it's because it's writing something to disk, and then it's got a lock file, you know?
Yeah, it's probably.
So I
because,
would suggest
yeah.
maybe just skip that
Yeah,
section,
because-
especially given time is already kind of.
Yeah. I think that
Um,
it will be more valuable to jump to the
But when
next
I
part.
ran that locally, it worked.
Yeah,
So it's only
I
in the
tested that
Navari
one,
that,
yeah.
for whatever reason, it has a trouble gathering these things. So I don't know if it's like somehow, maybe it's somehow using the GPU and then it's
Oh, yeah.
getting it back from the GPU, or,
Yeah.
I don't know.
Good catch.
Yeah, no,
I
I
can
mean,
skip
I was
that
running
part.
it earlier, so I
Oh,
was just
that's
trying to
good.
make sure that
Yeah,
everything
yeah.
ran on the Navari, and it's a lot faster, so it's good.
Yeah, I was running and I was testing that just before that, and it worked. So
Yeah,
I didn't
no, I
know
know,
that.
that's why, I did it multiple times,
Oh,
but I
yeah.
had to kill the kernel and restart from
Yeah.
scratch, so then it's really annoying,
Yeah,
because you
yeah.
lose everything, right?
You lose
So then you have to
everything,
go through everything one more
Yeah.
time. So I would just recommend skipping that section, so I mean, you may wanna just, we can just give people a heads up that like we're gonna skip it for time. But it's not,
Yeah,
it's
yeah.
not as visual, cause you're just
Yeah,
computing a
yes.
perimeter, so it's kind of like, okay.
Yeah, it's more valuable, I think, that the next part of that.
Yeah. Yes. So this one, when you're running it here, what we're doing is we're taking the data from the cloud, we're converting it to a NumPy array, and then running it locally on a single piece of the image, and then showing the image with this overlay. And then what we're doing here is we're actually processing it sort of in a parallel process. And so there might be some different model parameters that might be available. Let's see. So it's really just so the main difference is that we're not showing the underlying image. Yeah, so it's the same. If you what the problem is notice here, we show yeah. So what you're seeing here is a 50% opacity, but with nothing, without the backing layer underneath. So if you edit this in show labels cell to Dask cell, yeah, that'll,
So the actual is
yeah.
the same.
Yeah. But, was that code that you entered, or was it in the notebook?
Oh, that, right.
Okay, because otherwise we should fix it in the notebook, because that's a small little bubble. So you're basically overlaying over itself, and so that's why it's just turning dark, right? Because you're taking the image and putting it on top of itself. So this is correct. Yeah, you're showing it over the original image. No, the labels cell is the computed labels layer. So you have it correct. Yeah, see, that's the labels, so, which are integer values from 1 to whatever. And then what we want is, in order to show the colors, we're converting it to RGB. So here, you scroll up a little bit. So this is the output of a model.
Yeah.
So each object gets a unique number, and it's an integer image, right? So that's why it looks like it's going from blue to yellow. But what Fernando did here is he converted it from label to RGB so that you get the different colors. So in this case, it's an overlay of the RGB labels, different colors, on top of the original image. You can see the tissue slices.
Right.
And what you had here was an overlay of the RGB colors on top of the binary mask, which is why it was so dark,
Yeah.
because you weren't overlaying the image.
But the actual cells indication vectors is really just the same.
Yeah,
Okay,
exactly.
gotcha.
So what you want is to have the
But this
DA
is just
cell.
more like quicker processing, I guess, if it's a super
by showing it this way, you just see that particular object, but you don't have the pretty overlay. But at the end of the notebook, we do the overlay again. So here it is again. So we go back and forth. I think it's the, like, what do you want to look at, essentially?
Yeah, okay. I saw they actually produced it.
Yes. And you're running this locally, right, on your Mac?
Yeah.
Cool. And it's working?
It's working so far. I haven't got an error message yet.
Good. No, I mean, I ran it on mine as well. So,
Yeah.
so it should be leveraging the
I
GPU of your
worked on
machine too, 'cause you have a
video streaming data.
I think so.
I'm about to get
It's not
started. I haven't
immediate
played
though,
with
so-
it.
Yeah, but
Some of the things is that there are
so if you actually watch
participants in the video
so
data,
I actually never see it.
not actually
Really?
participants of the
Not
experiment,
much.
but
Well, maybe I
it's
missed it.
their
So-
oh, because you
relatives or
haven't, so
someone.
when you get to the later
So we
parts,
want
we're
to
going to do the whole
filter the
thing.
video
Yeah, when
And
it's
so
done,
you'll see the
maybe
tasks.
it will.
from
And
the
so the
data
limiting
where
factor on this computation
these,
isn't transferring the data from the
noisy
cloud, it's not
information is
rechunking it, it's literally
Um,
doing the segmentation.
I'm
And so the
thinking because
GPU,
I
like
run
on
out
my
of
machine, if
memory
I
and
come
things
to
like
it
that
as
doing
CPU only,
video data.
or GPU,
Do you
it's
have
about
any
like
idea, like, instead of segmenting,
and the difference
how
on this
to
Navari
find,
instance, if you run CPU only or GPU,
like the
is like a
particular
factor of 8.
frames that
So
are
you're speeding up
not
the
useful
longest time.
using some
And so as a result, when I run this locally on my machine, I download the whole ZAR to be able to do it on the
I
thing.
think that
But I also use the ZAR from the cloud at my hotel. And there's almost no mask
yeah.
because the transfer of the chunks is so much shorter than the processing that by the time the chunk is processed, 10 more chunks have arrived. So you end up, in this case, it's a perfect example of where the actual
I
data
have a-
is, you're accessing it piecewise in parallel,
I
and you're
I have
limiting
a
the factors, how quickly can you process.
version of the
So
data,
there's a pile of chunks
but I'm
to
wondering
be sent to the GPU.
how to access the
So
compression.
it's a really nice
So
example
if
of
I
using Dask.
decompress and make the
Because if
whole
you were
thing
to try to do it,
it's so slow.
eventually,
I only processed like 16 files and it took me
And if you break it up into
20 days
pieces and then run it, it won't
to
change
just
parallel.
process 16 files.
So like, using Dask in this case works
But
really
it
well.
doesn't make sense, like I
Is this
have
like a common?
about 400 videos.
I mean, it depends on the size of your computer. So if you have very
I
large
wouldn't be
images,
able to finish anything.
yeah, so if you're using really
So
large, so
I'm
in this
wondering
case,
what can
like
I
these full
do
slide images,
that is a compressed
100,000
file
100,000
to
pixels.
say
We're
that
just using
these
but geospatial
check out this
components
component
is that same
something.
thing. And so Dask is implemented with no sentences.
Because
like,
I'm not sure
you can't do everything. Think about it, the resolution of your monitor is something like 4K. This image is 200,000 by 100,000 pixels. You can't display that anyway. So you're always looking at either a piece of the data, just a small chunk, or you're looking at a downside. Because your monitor can't display 100,000 pixels by 100,000 pixels anyway. Exactly. Exactly. So these approaches that either downsample the data or rechunk it into smaller pieces are actually like really efficient. As compared to pulling the whole thing. Like another good example, I don't know if you've heard this new telescope launch, the Rubin telescopes. And so they have fantastic images of the sky, but you can download the TIFF. And it's a single chunk, a single TIFF that's like 70 gigabytes. And like you can do nothing. It's just one giant array. It's not chunked, it's not Dask, it's nothing. But on their website, they have a really cool loader where they've taken that TIFF and they've broken it up into dozens and dozens and dozens, hundreds of thousands of files. And you can actually load, zoom in, and navigate it. It's totally fluid on a web browser because it's not this giant TIFF, but actually tiles and tiles and tiles. Or if you use Google Maps, like as you zoom in, you see different resolution. And you don't load the map of the entire globe all at once, right? Because that would be useless. You don't care about that.
Multiple frames. You get a feature map of each frame. You can aggregate those samples.
Yeah, exactly.
You apply classification.
Do you know why I would get this error? I was just running through the delayed herpes skipped and copied it from the here, so it goes to the worker and then the worker's like, there's no such module as desktop distributed.
Oh, yeah, I think, so that might be, yeah, so I actually initialized Dask a little bit differently than Fernando did here, and I also got I didn't get the error, so I'm wondering, is the setup of the cluster? So actually, it's good that you mentioned. Let me me grab Fernando just so he's aware, because we might want to tell everyone how to solve this.
Yeah, I think that we are discussing there is any video, especially.
I'm trying to do some inference directly on the video compression, which is like extract the video files, the expression itself.
Maybe we can talk after. So we have, Fernando, we have an issue. So Nodar loaded there is, so you loaded the cluster a little differently than I did. And he's getting an error with worker being missing. And I loaded it a little differently. So I wonder if we need to fix it or announce it to everyone and let people rerun the code cell rather than, so maybe take a look at his error and I'll show you what my solution is.
So I mean, I initialized it the same way you did, sort of more manually instead of the extension, and then I was just running for the delay part, and I get this error where the worker complains that there's no module distributed in the task.
Are you on Navari?
Yeah.
Yeah, so I had the same error happen on Navari, but not when I ran it locally. And what I ended up changing was to, instead of use the get client, I did client local cluster and then client cluster. But imported
Yeah, no, I'm getting the same one locally.
Okay, locally. He's getting it locally.
I'm getting the same but locally.
You're getting that locally? Yeah. So we may need to, we may want to, we may need to, so that resolved it for me.
I think that we could probably go back and rerun that so everyone.
Yeah, I think you just restart the, the thing is if you restart the cluster, then it might, all the dashboards and stuff will need to be reset too. But I mean, if you go past that, will it work in the next section? It won't, right? The map blocks doesn't work either.
I haven't run that yet.
Can you try running the map blocks? Because I think it might also be just the delay part, and we're kind of skipping that section.
Yeah.
So if we could skip the errors, then we don't have to redefine it. Because if people want to use the dashboards, then we have to reconnect and all. I should have mentioned it before. I thought maybe it was just a single thing.
I mean, it's quite likely a driver thing. I found that I could get.
Yeah, looks like it is.
So maybe if we skip it, maybe we can get away with skipping
Yeah,
it.
it's a nice choice to skip it.
But so the solution is to my solution was to import from Dask distributed, import the client to the cluster, and then set up the cluster, and then instead of doing get client, to actually define the client. And I'm importing from Dask distributed rather than distributed. I think there might be some version difference, maybe that's at play or something like that. We'll put that in Slack regardless afterwards so that you all have it. But if we're skipping the section that has the problem, then we and if we're going to do another problem, then we're going to skip that section.
Yeah. So we can continue with this part. Before moving further, I want to show you that if you go to the Dask dashboard that shows you the task stream, you will probably see that there are something populated there. It is because we were running some selection from our Dask array, and it was actually triggering some computations because we were pulling that selection and computing the cell pose model on the NumPy that comes from the computation operation. Oh, what is this? Oh no. I was just talking about that and it disappeared. Come on. Where is it? Now I have many of this stuff open. Yeah, well, I still have this on the dashboard. What I was mentioning is that you could then here get a better grasp of what are the order of operations that are being applied, and you can inspect that what is actually like taking more time when using those. We're going to see this all illuminated when we start using the actual segmentation. So this is not working. So So we'll probably just restart the cluster, and we can actually see what how we can do that. So let me see if we still have access to the client. Oh yeah, so it just time up. So probably it's going to be good time to show what Peter noticed here. There is other ways other way to get the client. It is importing not only local cluster but also client.
I also imported from Dask.distributed
Oh,
instead of
okay.
distributed, which may also be part of the solution.
Yeah, I would think that it's the same, but yeah, it's something has to change there. So I'm running this to get a cluster again. So instead of using the get client, it is I think it's overload that we have client from the cluster, and it's going to be the same. Oops. So you have the. I would probably need to change this because every time it spins off the cluster, is going to try to get a random port. So I'm going to replace this here to have access to that again. And I will need to re-import this stuff. This. It's probably just the first part where we format our array to get access to that. And where we import our model too. So it was not that far. The idea is that we want to grab this operation that we did here into something that we can call individually for each of the blocks in our, or for each of the chunks in our image. So I'm going to bring this stuff here. So basically, I'm going to grab this into a suppose inference. I'm going to probably chunk. So we know that this is applied per chunk. It receives an image chunk. We can tell it either we want to use or not the GPU. So by default, I'm going to set it to false. The model type, we are going to set it by default to the Ceto tree model. I think this is enough to that. So I'm going to paste this here, but I will need to modify some parts of that. But I'm going to come to that later because I need to pull these operations and paste those there too. So I'm going to copy this. Those are the pipeline of preprocessing that we apply to the image before passing that to the model. I'm going to paste those here too. And just make sure that instead of applying to this, we are applying that to the image chunk. Oops. Come on. IMG chunk. Okay, and then where are my notes? Basically, what we are going to return here are our labels. And there is an additional step here that I want to add, and it is, as you can see, this model is going to be loaded every time that we call that for each of the chunks that we analyze. This is because otherwise it would be having a global model that is passed through the network to each of the workers, but then you have this overhead of passing, if it is like imagine that it's a 50 megabytes model. You have to pass those 50 megabytes model to each of the chunks that are applied. So there is a way to actually get like some caches for each of the workers. So I'm going to use this worker is Dask distributed dot get worker. So when this function is passed to a worker to process, we can get like some ID or like features of that worker that is being used locally. So if you think in parallel, each of the workers are going to get their own information. Then there is this with worker dot underscore lock that is like sorry, locking the operation of doing this. So each worker has to do that by themselves. And there is now this checking if there is already a cellpose model in the worker, use that. Otherwise, create a new model and use this new model that was created. So I hope it makes sense with we implement this. So we check if there is inside of worker an attribute that is called cellpose model. And if not, well, just let's create a cellpose model with these specifications that we passed. And so this is only going to happen once. It's going to be cached for each of the workers. So each worker has an existing cellpose model. Because it's inference time, we don't need to update the model. So there is no risk of applying that, and the model should be different for each worker. It is the same model. The only difference is that we don't have to pass that through the network every time. Okay, so if you can see, this is just a regular Python function that receives a array-like.
I think you might need to rewrite distributed, perhaps.
Oh,
Yeah, type out distributed.
Oh, thank you. Yeah, this is why I stopped functioning.
Fernando did that intentionally to see if we were.
Yeah. So I think this is everything that you have to apply here. And as I mentioned, this is something that is just defined as a regular Python function. And we are going to use this function to apply with, distribute that with the map blocks function to all the chunks that our image has. So I'm going to go, I'll have this function already implemented, because you can copy that from the solutions. What I wanted to go is probably just jump to this section and use this function that is inside Dask array that is called map blocks. That is basically doing that. It's going to map a function across all the blocks or all the chunks that are inside a Dask array. So I'm going to call this DA labels. So DA map blocks. And then we are going to pass there this cellpose segment. I call this segment? No, I call this inference chunk. Cellpose inference chunk. Oops. Oh, come on. Chunk. Then we need to pass the inputs. So the first input is the array where we want to apply that. So this is the Dask array that we have, lazily loading our image from Cloud bucket. And then we have to pass there any other arguments from our function. So for example, the GPU and the model type. So GPU, we have defined this before. So I would say that we can use this from the previously defined variables. And then there is this important part that we have to add when using this function, that is understanding what is the output that we expect to come from this function, because Dask mapblocks function does not know how it's going to be modified inside the function, this array, so we have to give some insight. So for example, we are taking an RGB image, and then we are getting a two-dimensional output array without any channels. So we are basically dropping one of those axes. So this is something that we have to tell the map blocks. So drop axis. So we know that we are going to be dropping the axis index 2, that is the assigned to the color channels. We have to do that as a tuple. So even if it is only one axis that we are dropping, we have still to define that way. We need to define here what is the data type that we expect to have. So numpy is int 32 bytes. And then importantly, to prevent doing some extra computations and probably some of the errors that I have faced when using this without the meta argument, is passing here an empty numpy array. So it doesn't matter the shape of that. What it matters is the data type that we assign here. So this is an integer 32, and that's it. So if we don't specify the meta, it is going to create a zeros chunk. It's going to pass that through our function, and it's going to try to determine if the data type and the axis are correctly defined by what we have passed to these specifications. There are probably some functions that expect actually have something in the image or in the array, and so you don't expect to have zero arrays, and it might fail. So just to save that operations, you can specify this meta argument here. So if you run this, and you inspect what is generating, you can see that it is not still computing the full segmentation, but we now have a Dask array that can compute the self-post inference on the whole image. So I'm going to show here that we can compute that on a region of the image. So pltm show DA labels, and I know that there is something in these coordinates, 8,000 plus 512 and 2,000 plus 512. Is this? Oh yeah. So it is complaining because we are still loading the model in the. Oh no, sorry, I don't think so. Oh yeah. So this is why we have to cache the model inside our workers. I didn't notice that I am not applying the self-post model from what we have inside our worker. So we are taking the global self-post model, and this is trying to pass that through the network. And so this is why it is complaining that it can compute that. In some cases, it's going to fail. But if it can anyways compute that, it's going to complain that it is still trying to move this object, this is the model, through the network to each of the workers every time that we compute a different chunk. So to prevent that, just make sure that you are using the worker dot underscore cellpose model. I'm going to rerun this. Come on. And run this again, the map blocks. And if we do this, I wouldn't expect that to happen again. Okay, so the warning is not showing again. And basically we see here probably this like chunked version of the inference. It is basically because we are applying that inference step to each of the chunks, and when applying that, it's probably losing the edges of the image in the inference step. This is something that we'll need to, instead of passing the image, we'll need to pass like some overlap of the chunks that are around that specific block every time, so we can like compute the segmentation with this overlap around it is called a halo around the current chunk, and we'll need to like crop that again so we know that we are returning the same input again. But again, this is like if we increase the size of the chunk, again, if we have a capable GPU, this issue is going to be probably negligible because we are just computing this on big chunks, and we are just losing like some small edges on that computation. So it depends on the task that you are doing that you will probably need to pass into the other version. It is again a Dask array map overlap function that it is similar to the map blocks, but you need to add other considerations to that. And so we're just going to stick with the map blocks.
You have 20 minutes.
Thank you. I think that we can jump into the actual computation of this, because I know that because we are running on the GPU, even if it is the full image, it shouldn't take that much time. But I would like to show you that you can like integrate this idea of applying the chunk inference process along with that mask that allows you to just compute that on specific regions that you know that contain something of interest. So if you remember, probably the image is, it has a lot of background and white space that you don't want to waste time computing on those, because you know that already that there is nothing there. So we would rather compute on a masked version of that image. So I'm trying to check that. How much do I have to copy from that? I'm going to show you what I want to achieve there, but I think that because of the timing, we are going to end just running the full map blocks. And this is fine because it is a cropped version of that image, and it's not going to take that much time. So what I was mentioning is that you can, for example, access to a lower resolution of the image. So instead of getting the full resolution, you get to 2 levels below. So it is a smaller version of that image. So instead of being this huge 30,000 by 40,000 pixels, it is just 700 by 700 pixels. So it is a downsampled version of the image. And we can compute like on that rather easily than compared with the full image. So we can operate on the full version of this downsampled version. So this process is described in the solutions. It's basically the idea of creating a mask from that low resolution and then extrapolate that into our full resolution image. So what I'm going to show you is what we're going to achieve there. It is basically creating this very low resolution mask that each of these elements in this array are correspond to one block in our full resolution image. So you can think that you can pass this through the map blocks and have an initial comparison step where you can check if there is anything in this mask, compute the inference step that sometimes is the bottleneck of the process. If there is nothing in that mask, don't waste time, and then just return me a 0 array of that shape. So this can save a lot of time, especially if you have like bigger images that contain just small regions of those are actually content, and the rest is background. So to do that, there is this nice part of Dask that you can like pair, even if those are not of the same size, you can pair two different arrays that share the same number of chunks, and you can pass those to map blocks, and it's going to take a chunk from the full resolution image and a small chunk from the mask, and it's going to compare that, apply that comparison. So this is what we would need to do. That is checking if the mask is if it contains something or not, in order to actually apply the model. Otherwise, just fall back into create a zeros array and return that as the labels output. So, but the interesting part is actually like computing on this. So we have not triggered the computation, and this is because we don't want to move everything into the RAM memory still. Even if it is this like lighter version, it is only 1.26 gigabytes labels. We still don't want to move everything into RAM. It would be more efficient if we directly create a file from this. So I'm taking this one, okay, and I'm going to import something to, I think it's not going to work anyways. If you are running this locally or without the Dask extension, it works if you pull from Dask diagnostics, you import progress bar, and it's going to give you like a very nice diagnostics. It's going to give you like a nice progress bar when you are computing on your Dask arrays. Otherwise, I think that because it is using the Dask extension, is just falling back into showing you the task graph here. So anyways, here we will want to store again this array on disk. It doesn't matter, I think, if we operate on that fully. So what we are going to do is call from our labels Dask array the toSar method. So we need to give here like the path where we want to store the output. So I'm going to call it cmu1 crop labels suppose Cyto3. So give a meaningful name so we know what we apply to generate that image. And then we want to store this in the component 0. So this is the segmentation on the full resolution image. We can pass there arguments that go directly to the SAR function that creates the file. So for example, write empty chunks equal false. So this can save time if you go through the mask approach. You don't have to, if there is a chunk that doesn't contain anything, is not going to create a file in your file system. I think that if you're paying for storage, it is important because storing empty chunks is not going to be very efficient. Then you can apply, for example, or pass the compressor that you want to use, compressor. And for this case, I'm just going to use the Dask compressor that comes in SAR and give a very high level of compression, because this is what we are storing are basically a mask of labels. So I think I'm ready. So this is going to trigger computation, and we can move into the dashboard to see what is happening there. So I'm going to run this. What is this? Oh. There is something already there that I probably left from previous tests. So there is the overwrite option that you can also pass to SAR. So whatever is there, just overwrite it. So this is running. I'm going to go to the dashboard to see what is happening. So first check the workers. They are working with almost 100% of CPU utilization. I'm going to check the GPU, for example. So it is at less than 4.5 gigabytes from the 16 gigabytes that it has. And check the task stream. And you can see here, if you point your pointer on these blocks, it's going to tell you what is the operation that is taking in that moment. So for example, you open here, the bottleneck is this cell post inference chunk that is what basically we are playing the inference part on. And it is taking less than a second in some times. It depends on, again, there are some post-processing. If the image, if that specific chunk contains like more objects, it's probably going to take more time to process because there are some post-processing steps happening. If it is rather like these cases, there is nothing there, it's just faster because it skips those steps. There are other intermediate steps here that we can see. They're basically from SAR. So it is basically the pull operation from the cloud storage. And you will see if we zoom in other operations that are going to be the rechunking, the selection of the channels, and the storing process. I think there is a way to also show you the overall task processing. I'm probably going to use this dashboard because I know it's better. This is from a previous run, so it's not going to work. So I'm looking what is the name of that before it finishes. Aggregating production. So this is like some profiling tools that you have in the dashboard. And I'm looking for the task scheduler system. Graph. Yeah, I'm going to use this directly because I'm more used to go directly to the dashboard. So this is what I wanted to look for, and I don't know the name of this specific widget. It is just showing the progress of each of the operations. So this is what you can actually refer to when thinking how much time or how much progress is doing. Is the there is a to-sar or store map. The store map is the actual creation of the file in the file system. So this is ultimately what is going to tell you if the process has finished or not, because it's the last operation that is applied on the full graph. But anyways, you can see here other part is that we are distributing the process across the workers. You can have a better idea of the utilization of the memory. So if you could probably use less or request less memory for running this cluster, you can do that by looking at what is the historic utilization of memory. And basically, this is like operations that you can apply on Dask to parallelize these kind of tasks. So I have 5 minutes, so it just finished on time, and yeah, I don't know what is this. This probably some warnings from the cell post. Oh, I have to check that. But what I wanted to go through after that to show you like the actual power of this. Probably for now we are having just seeing graphs and small representations of the image. So I'm going to copy this. This is in the solve on the solutions of the notebooks, just because we are running out of time. There is I basically created a small pipeline to create downsamplings of this image. So we only have the full resolution labels, but we can rather like create parameters for that, so it can help for visualization. So if you open this in a viewer, you could access to like a downsampled version, so you can zoom out and still have don't have to pull the full array of labels. So if I run this, I think I'm going to run this. So what I'm doing is we now have a stored local version of this array. So we can now, instead of running the segmentation process, there is no sense of using that. We can just use whatever we have already computed. So this is pulling from the local copy of this the label cell outputs that we generated, and this uses subsampling multiple times on different levels in factor of 2, and creating this multi-level, multi-scale version of the labels. So what we can do with that is, for example, showing an overlay that we have done before for a specific region. I have to, of course, load that. So load our SAR file, and then we can access actually now the labels and compare that with the overlay that on top of the actual image. And this is what we have done now. So I am showing you this like bigger crop. It is a 4K by 4K, and we have done this for the full image. We have not used more than it was 1.5 gigabytes per worker, and we have achieved that with no more than 4.5 gigabytes of GPU utilization. So we have pretty well utilized this cluster just to apply these inference operations that otherwise it would be just prohibitive to send the full image to cell post and wait to that to be processed, because it is processing the whole image at once. And just to show that there is actually the full image that has been segmented. I'm just showing this. We didn't run the mass version, so it is the brute force of applying the inference. So we have here some noise. But for the actual pieces of the image that contain tissue, it is applying the function to that. So this is the whole image. I'm just pulling a downsample version. But we can just open this in a viewer, and we could have a better grasp of this. So you give me 2 minutes instead of just the one that we have. Oh, come on.
And remember, this raw data started in the cloud. It was uploaded by me in Connecticut into the cloud, and now we all streamed it to our machines, processed it in the Vari or locally, and have the output. It's pretty remarkable.
So probably you are familiar with this.
Perfect opportunity for Vari.
Yeah, I forced Fernando to add that.
At the very end, we really have to show this off.
I forced him to do it.
So I will probably, I have a copy of this when I was running that. So there is, of course, an Apari OME SAR plugin, so you can open SAR files that are, yep.
Yay!
This is probably need to change it to, what is it, convert to labels.
Yeah.
And you can see that these are the pure labels. I can open the file, the image file. Because I have it somewhere in.
There is instructions in the, if you go to the rendered docs, there's a little, I made a little one page that shows you how to do it.
So I hope you have learned something. I'm sorry because I have to like skip all the exercises, and it was more like a demo, guide demo. But I hope that you have like grasped the idea, and that these nice libraries can be put together to achieve this. So I don't know if you have any other questions about this. Yep.
I got a few technical ones, but one is about self-pose and, or I guess, chunk operations in general. You self-pose like operates on a chunk and then spits out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 integers, and then it goes to another chunk. How does it know to use different integers for the next? How does it know to separate out the integers, the labels between chunks? Do you have to specify that, or is that implicitly known somehow?
No, that is something that, you can imagine that each block is going to start from 1 to n objects. And this is the same issue that probably this would be an intermediate step. Next step will be merging all those together. So you can, there is like a relabeling operation. And I think that there is in Dask image already this operation implemented. So this is basically taking each block, because each block has their own indexing from 1 to n objects, is going to try to merge all those. So you have a single that, or you can probably engineer a way to know, because you can know where in the image is this chunk being computed from. So you could probably add some offsets already from those locations, and at least you don't have clashing indexes. Or you could probably do just some sort of random indexing. Some of those segmentation approaches are just intended for a single patch. So they were not thinking on applying that to a whole image level anyways. So thank you.